Okay. It seems to be doing okay now. I don't know why it screwed up that time. Okay. Let me see while I was doing that if anyone else added the class. They have not, just the two of you and me. Okay. So we're going to get started again. Okay. If neither of you have any questions, well, I think I will just inform you of what we're doing. We're in chapter 6 and section, I believe it is 6.4. The title of this is Electric Currents and Magnetism, and we're right now talking about electric motors. That starts on page 161 in the big book, 6-22 in the smaller book. Okay, we will cover hopefully the rest of this chapter today. I think we can do that without too much problem. When we finish the chapter today, rather than starting chapter 8, since we have 3 classes to do chapter 8, the 2 days after Thanksgiving, that week after Thanksgiving, and then the Tuesday of the following week, that's technically a class day for second mini-terms classes. It's final exam week for full-time classes, but it's a class day for us. So we will have 3 days to do chapter 8. Hopefully we'll get that done with no problem in those 3 days, and then I will give you your final exam. So we'll see how that goes. Today, after this class, we will have a lab, and that will be the last lab for chapter 6. Okay, and I think we can probably get 2 labs done for chapter 8, one on Tuesday and one on Thursday. Now, and then there won't be a lab on the following Tuesday because you probably have the chapter. Okay, here comes Daniel. Let me get him in here. And that's good to see. We've still got people coming in. And Daniel's here. Okay. So increase the class size by 50% that time. Let me just make sure nobody else is coming in right now. I don't see anyone. So we'll go with the 3 of you. Now, Daniel, I don't know if you're in yet. Can you hear me?
Yes, sir, I'm in.
Okay, good. Do you know if the other 2 guys from GM's are coming?
Yes, is that we had a drop from Birmingham to Gunnersville, Alabama,
Oh,
about an hour and 45 minutes away, so we're all coming a little late.
oh, I see. Okay. All right. Well, then um, I'll try not to repeat this every time that somebody comes in, but I'll probably wind up repeating most of it. Okay. What we're doing now, we're in chapter 6. Hopefully, we'll finish chapter 6 today. We're in 6.4, which is electric currents and magnetism. We're on page 161 in the big book, 6-22 in the smaller book. The part, as you see on the screen, that starts electric motors. Okay, hopefully we'll finish the chapter today, and then we'll do the lab today, the last lab for chapter 6. It's already posted out there under this week. I think this is week 6. Okay, and we'll get to that later. Now, that next week, I guess all of you know, next week is Thanksgiving week. There are no classes during Thanksgiving week. Now, that doesn't mean the school's closed. The school will be open. Offices will be open. You'll be able to take care of business Monday, Tuesday, and Wednesday. Now, the reason I hesitated on the Wednesday part is that the Wednesday, day before Thanksgiving, a lot of offices or administrators or whoever will start letting people go. Probably sometime Wednesday afternoon. That's not guaranteed, but it's just sort of a habit. It's kind of a thing that usually is done right before Thanksgiving. Now, so if you have business to do with the school, you can certainly do it. All the offices will be open Monday, of next week. They'll be open Tuesday of next week, and they will be open Wednesday morning of next week. They probably, many of them, and maybe some, maybe even most of them, will be open Wednesday afternoon as well, but I will not even begin to guess how long they'll be open. So I would say if you have any business to do with the school next week, get it done Monday, Tuesday, or Wednesday morning. Okay? So we will be, everybody is required to work unless they're taking personal leave or something like that next week. So I will be in the office here, this upstairs bedroom. Okay, but I think are going to be required to be in some type of professional meetings. So we may not be reachable except during certain times in between, you know, activities, whatever they have planned for us, which usually is sort of dorky. I didn't say that out loud, did I? Okay. But anyway, there will be times. Now, Wednesday afternoon, if they finally let us go, I will try to continue working. Now, my wife may have other ideas that I might need to be helping her do some cooking, and I don't mind doing that either, but I will work as long as I can get away with it. Okay. So, that's next week. The following week, after Thanksgiving, we come back. We have classes Tuesday and Thursday. This class does. And we'll start chapter 8 on Tuesday and probably have a lab on Tuesday. And then on Thursday, continue in chapter 8. And I think we'll probably have a lab for that one as well. We'll see. Okay. And then the following week, that is the Tuesday is still a class day for second mini-term classes. It's a final exam day for full-term classes, but it's a class day for second mini-term classes. And then at the end of that, hopefully we'll be through with the chapter 8. I will not do a lab that day because I don't want you having to turn in the lab on the last day, final exams and stuff like this. I don't want to have to grade them and that kind of stuff. So we won't have a lab that last Tuesday. But I'll probably give you your chapter 8 test and give you the final exam also. The final exam will be very short, very easy to complete, and not very much time. So don't sweat having two tests at the same time. They will be pretty easy. Now let me go back and say that at the end of class today, after we finish the last lab for chapter 6, at some point I will post the chapter 6 test also. So you'll have that. So you'll have something to work on during Thanksgiving week. I know you would just be terribly depressed if you didn't have some physical science to think about during a whole week off. So I'll make sure you don't get that depressed. Okay. Any questions, ideas, anything about what we're going to do? Okay. Now, I'll probably go through some of that again as more people come in, but then I'll save another part for a little bit later. If we finish the class today early, we won't start on chapter 8 because I don't see any reason to have such a big long break between the beginning of 8 and the end. So we'll go on and start on the lab when we finish the chapter today, and then if we finish the lab early, that's just too bad. You get cheated out of your tuition dollars again. Okay, so any questions? All right, now a lot has happened since we met last time, and I wait for more people to show up, so I only tell that story once. Okay, so let's start on electric motors. Now what electric motors do is they convert electrical energy that come from generally batteries or power supplies like your plug in the wall, and they convert that to mechanical energy because a motor turns something. Okay, it could be your weed eater, it could be your electric lawnmower, it could be your starter on your car, it could be anything such as that. But all electric motors act pretty much the same way. What they have is a field magnet. Now this is very similar to what we saw when we were talking about meters in the earlier illustration. I'll click back to that. There was your field magnet. the north on this side, the south on that side. That establishes a fixed magnetic field. Remember, the magnetic fields go from north to south. They point from north to south. And that's a very strong, pretty consistent field. Okay? So let's go back here to your electric motor, and that's exactly what's happening here. You have a north pole here, south pole here. Your field, magnetic field, is cutting across pretty much from north to south. A very, usually fairly close to parallel field lines going from north to south. Okay, so there's your field magnet. You have the armature, which is your movable electromagnet. Now, it's on an axis. The axis is this circle here that's coming out of the board into the screen. That's your axis there, and that's movable. Okay, that's what turns. Okay, turning the axis. Okay, now why does it turn the axis? Well, if it's set up like this, like you see here, this is a fixed north pole on your field magnet, fixed south pole on the field magnet. Your electromagnet, the way it is drawn here, is giving a north pole here and a south pole here. This north pole is repelling away from that one. This one's fixed, so this one is trying to move away. So it's turning in this direction, making the axis turn at the same time. Okay? The south is also being repelled by that south, so it's pushing away, so that also is turning the axle this way. Now, if that's all there was, folks, then this would turn around and line up with the south pole, this would turn around and line up with the north pole, and everything would quit. But it doesn't happen that way. The armature rotates, that's what this is called, the armature, the rotating part, by interactions with the field magnet. Now, right in here we have what is called the commutator. Now what the commutator does is change, it's called a split ring commutator. In the old days, that's what they called it anyway. And on that commutator, as soon as these brushes, and they don't really describe them very well, as these brushes turn, the armature turns against the brushes, when it gets halfway around, which would get this north lined up with that south and this south lined up with that north, maybe just a tad beyond it, then all of a sudden the brushes touch a different part, the opposite part, because there's a gap here. That's what the dotted lines are representing here. And that gap, in the gap, when the armature turns, it changes the polarity of your electromagnet. And by changing the polarity, suddenly this north pole here that had turned around and lined up with the south, and this south that had turned around here and lined up with the north, they suddenly change polarity because the wiring, the electric current starts going in the opposite direction. That's what the commutator does. It flips the direction of the current. So suddenly that becomes a south pole. This becomes a north pole. Now they repel again, and they keep moving and keep moving and keep moving. That's what makes an electric motor work. The commutator and the brushes reverse the current to maintain the rotation. And then when they get a halfway time around again, and this that has now become a, let's see, where were we? This south has lined up with the north lined up with the south, and right then it changed polarity, and now this becomes a north and that becomes a south, pushes away, it changed the polarity, pushes away again. This keeps turning and turning and turning. Every half turn, the brushes change directions of the current, making the motor work. And guess what? There's not a lot of friction. There's not a lot of energy loss. There's always a little bit. Remember, second law of thermodynamics, always some energy loss, but generally electric motors are pretty efficient. Any question on electric motors? Okay. Now I just can't believe we don't have but 3 students here, but that's all we got. Nobody's in the waiting room. So let's move on to electromagnetic induction. This is flip a page to page 162, and this now is a new section. We're in section 6.5 now, electromagnetic induction. Now I just want to do a little quick review with you here. What is it that creates a current? Electric field. An electric field is created by a moving charge. Always. The Earth's magnetic field, I said it backwards. A magnetic field is created always by a moving charge. The Earth's magnetic field, inside a permanent magnet made out of iron, nickel, or cobalt, those are the only 3, remember, those atoms have moving charges in them, okay, and moving in such a way that it sets up a fixed magnetic field that for some reason is not canceled out by anything else. The alignment of those domains. We talked about that before. Okay, so that's what creates a magnetic field. Well, guess what creates an electric current? A changing magnetic field. So a changing electric field induces a magnetic field. Changing magnetic field induces an electric field. So the causes of electricity is relative motion between the magnetic fields and the conductors. Now when they say magnetic relative motion, that means on the one hand, and we'll see this a little bit later, you could have a fixed coil which represents electric and a moving, changing magnetic field that would create electric current. Or you could have a moving magnet I think I just said that, okay, a moving coil inside a fixed magnetic field. Either one of those. In fact, this that we had right back here, if I could get it to come back, come on back, brother. Okay, yeah, you see you have a moving magnetic field within, moving, well, this was not creating current, but you have movement within a fixed magnetic field. And we'll talk about that a little bit, so hang on to that concept, okay? So all it needs is relative motion between the magnetic fields and the conducting wires. The changing magnetic fields near the conductors causes the electric current to happen. Now here we have a coil of wire, okay? And here we have a coil of wire, identical coils of wire, identical. In this one, we have a magnet moving down in the coil. Now notice in this coil, there is absolutely no battery, no plug in the wall, nothing, just a coil of wire hooked to and you can't tell for sure, let's just call it a voltmeter, okay? It could be an ammeter, but they're going to act the same way, okay? A voltmeter. You drop this magnet through that coil of wire. When that, okay, let's imagine this north pole of this magnet is up here somewhere, not influencing the coil at all. So the coil has got 0 magnetic field lines being cut, nothing. This voltmeter or ammeter is sitting right on 0. Nothing's making anything move. Not plugged into the wall, not connected to a battery, nothing. Okay, 0 voltage, 0 current. As that north pole falls through this coil of wire, it is increasing the number of field lines being cut by those wires. And as that happens, that produces a positive current. Okay, we're going to assume that's positive. Okay, now if you had continued, and they didn't, and watch that south pole fall through that, then you would have created a negative current, probably about the same amount, because these two have the same field lines around them. So it's anytime you have relative motion of the field lines, the magnetic field lines, and the coils of your conductor. Okay. Now, on the other hand, what if you had this magnet moving upward through that field line, that coil? Well, again, your south fields would be breaking this, changing field, moving through a coil of wire, produces a current. Again, the south pole produces a negative current. The changing north pole, if you let this go on longer, it would then pop back here and become a positive current. Okay? Now, those are the causes. Relative motion between the magnetic fields and the electrical conductors. Changing magnetic fields near conductors creates current. Okay? So what's the effect? Induced voltages and induced current. It creates a voltage, it creates a current. No battery in sight, no plug in the wall. That's how you make a current. Okay? Now, the induced voltage depends on three major things. Number one, how many loops are in that coil. Okay? Very few loops, you're going to have pretty weak voltage and current. Way many current loops, you're going to have stronger and stronger voltages, higher and oh, here comes Angelita. Okay, good. We're finally getting some folks here. Okay, hopefully they'll keep coming. So Angelita is here. Okay. Now, Angelita, I've already made some comments about how we're going to wrap up today. Not next week. Next week's Thanksgiving week, but the week after that, and then the week that the Tuesday is a class day and the Thursday is finals day. I will wait until we have more people in here to repeat that, probably right around the end of class time, beginning of lab time. I'll make that statement all over again. So we're right in the middle of electromagnetic induction, which is on page 162 in the big book, 6-23 in the smaller book. Okay, and we just had finished talking about this, and I'll just rehash it real quickly for you. As we talked about before, a moving charge induces a magnetic field. Every magnetic field you'll ever see, in a permanent magnet, electromagnet, fixed magnet, the earth is a magnet, any magnet that's out there is created by a moving charge. Okay? Now that may be in submicroscopic domains of iron, nickel, and cobalt. The moving charges in those three elements do create magnetic fields. Now, what we're doing with electromagnetic induction is saying that the relative motion between a magnetic field and a conductor, electrical conductor, creates voltages and currents. Okay, so yin and yang, changing a moving charge creates a magnetic field. A changing magnetic field induces a current, which is a moving charge. Okay, so let's go to the next slide if I can get the, well, let's see. Yeah, before we hit generators, in Concepts Applied on page 162 or 6-23, there is an illustration of a simple generator, a description of that, Concepts Applied. Read through that. I think you'll find it pretty interesting and go from there. Now, there is another little blurb at the top of page 163 and they said current war. Now that doesn't mean a war that's going on right now. That was a fairly major disagreement that was occurring early in electricity's life, okay, or manufactured electricity's life. The earliest, and he was a brilliant engineer and scientist, Thomas Edison, probably did more with electricity than any other single individual ever. He has, I think, close to, if he doesn't have the record on patents, at least he does on important patents. I think a lot of people get out there and just write patents on just about anything, most of them inconsequential, or a lot of them inconsequential. Thomas Edison's inventions were historic, okay, folkloric. They were just amazing. But Thomas Edison firmly believed that direct current was the way to go, that alternating current was very dangerous. Okay? Well, there were two other guys that thought differently. One of them was named, I'm surprised they don't mention him. Yeah, there he is. Okay, George Westinghouse, who was mostly a businessman. He may have done some invention and stuff like that, but he was actually 1 year older than Edison, but he didn't live nearly as long as Edison. Um, but then this young guy came along named Nikolai Tesla. Now, if you think that's an interesting name, it said he was Croatian born. I don't know if y'all know where Croatia is now. It used to be part of Yugoslavia. So I bet you he was Yugoslavian born, but they may not have even used that name then. But anyway, he was about 9 years younger than Edison. He came along, he worked for Edison for a while and worked with Edison for a while, but after a while they broke ranks because Tesla and Westinghouse were both convinced that alternating current was the way to go. You just could not generate strong enough direct current to go very far. You had so much line loss. Whereas you could moderate and change alternating current. So that is an incredibly interesting little blurb. This blurb cannot be the source for your paper. However, it can give you ideas for the source. For instance, who in the world was Thomas Edison? What are some of the things he did? Who was George Westinghouse, and what are the things he did? We recognize the name because there's a company named after him that I believe he founded. And by the way, Edison also founded Con Ed, Consolidated Edison, which is still a power company up in the Northeast. And Nikola Tesla did not found Tesla, okay? They named Tesla after him, the company Tesla. He actually was not a very good businessman. He had incredible, great thoughts and ideas. However, he could not commercialize them as well as the other two did. So anyway, several potential paper topics in there, including the one on the current war between AC and DC. All right, with that done, let's move on to generators. Okay? Now, what are generators? Generators are basically a backward motor. Okay? Whereas a motor converts electrical energy into mechanical energy, a generator has an axle, main wire loops, magnetic field. The axle is turned mechanically. Here's the difference. The axle is turned mechanically and it produces electrical energy. So whereas a motor takes electrical energy and creates mechanical energy, a generator takes mechanical energy and produces electrical energy. Okay, that's the difference. Okay, the ingredients are still pretty much the same. You have an axle, you have wire loops, and you have a magnetic field that somehow is changing. Okay, now we'll mostly picture AC generators, but we'll tell you how to get a DC direct current generator out of that. So let's start with alternating current. Now, what makes it alternating? the signs of the current and the voltage alternate. And I mean, they alternate incredibly rapidly. Something like they change about 60 times per second. That's, I mean, so there's really no net current flow at all. The electrons or the charges just go back and forth, back and forth, back and forth, because the field is constantly changing at a very rapid rate of speed. So here's the picture of the generator. Okay, now what we have here is a field magnet, north pole here, south pole here. So there they drew in the field lines for you on this one, and they're almost parallel field lines. Okay, that's fixed. That's right there. Okay, that is your field magnet, they call it. Okay, out here you have something turning an axle. So this is your axle out here. Now, if you think about this, as you turn this axle, now these field lines are constant. But you see right now, the way they have it oriented with that loop, you might say, right in the middle there, and perpendicular, it's cutting the maximum number of field lines. But you have something turning this. That turning could be caused by water over a dam, like in a hydroelectric generator. It could be steam turbine that you have in a coal-fired, natural gas-fired, nuclear power plant, anything that is moving steam through a generator. That could be it. It could be a wind turbine. It could be anything like that is turning this axle, and that makes the field, the coil turn. Well, when it turns, it goes from a large number of field lines being cut to a smaller number, until 0 field lines are being cut. But then they start increasing again, then they start decreasing, and then 0, and then increasing, decreasing. Now, what's happening then, as the number of field lines being cut is decreasing, you create current in one direction. When it goes to 0 and then they start increasing again, it creates a current and a voltage going in the opposite direction. So you start off here. Now this isn't starting where this is. They would be starting at the maximum here. So you'd be starting up here. And then as it turns and goes horizontal here, then you go down to 0, and then as it continues to turn, it goes negative, and then as the number of field lines being cut in the negative direction reaches its max, that would be exactly opposite of what you see here, then they start decreasing again, which is decreasing the magnitude of the voltage here, and it goes back to 0 when it's flat again, and then starts the process all over again. So these are your terminal brushes. One of them's touching this, one of them's touching this. For half of the cycle, it's positive. For half of the cycle, it's going in the negative direction, alternating every time it turns. Every time it turns half a turn, okay, that's your alternating current. Because this thing, every time it cuts and starts increasing, decreasing, it changes every time it reaches 0 and starts going, the current goes through this thing in the opposite direction. Now, that's an AC generator. Most of the time they just call it a generator. What a DC generator does, it has to flip right here. It would be positive for half of a turn, and then right when it would go negative, it has to flip it to send it back in the positive direction. Your sign of your current and your voltage always stays the same. It's not a constant pulse, it's a pulse DC, but it is direct current. And here's how they look. Okay, same field magnet, same axle, same coil. The difference is you have again a split ring commutator. Now here's what's happening then. Before you had solid rings, one going one way, one going to the other. This time you have a split ring, and this is sending current through the connection here. This one's sending it here. You have a gap in the middle, and when this is being turned and you're got a positive current here, then, or positive voltage, that is touching, say, this side, and the negative is touching that side. Okay? And then right about the time it goes from zero and flips to change its direction, then it goes to the opposite ring, and then this one, which would have been doing, if this one initially was positive and this one initially was negative, and that goes to zero right there when it gets flat here, and then when it turns it a little bit further, this one would have gone to negative, that one positive, but now it's no longer. It flips over to the negative side. So now it's negative again. This one has moved to the positive side, so you have a pulsed direct current. Always positive. It's varying, but it's always positive. Never flips negative, because that split ring commutator happens right at the place where it would have changed sign and gone negative. And then when it goes over here, half a turn again, it flips again and goes positive again. And then again. And then again. So it keeps doing that, and that always keeps your current and your voltage to be in the same direction, generally positive. Now, we've only got one auto mechanic in here, and I don't think they use split ring commutators anymore. They use something like dual diodes, but where does this show up in an automobile? Do you know? It actually is named, to me, a little backwards. It's in your alternator, or do they even call it alternator anymore? In the old days, that's what they called it. What is happening there, your engine is turning, and that engine is creating somewhere in that engine you have a small generator. Okay? That generator is producing electricity. What that electricity is being used for is to recharge your battery. Because when you turn that switch to start your car, you're draining energy off your battery to turn that starter motor. Okay? That battery is DC, direct current. Okay? And that starts your engine, and then once your engine picks up the momentum, the flywheel, the pistons, everything else keeps everything moving. So you're not using the energy from the battery anymore, unless, of course, you turn on the lights or the radio or things like this. And I don't know how they wire the cars, whether that's coming straight from the generator or if it's going through the battery. However, but anyway, you need to recharge that battery. So your generator does that, but your generator produces AC. Well, that wouldn't recharge your battery. It would recharge half a cycle and discharge, recharge, discharge, recharge, discharge. Wouldn't give you any net thing, any net direct current. So what you have is, like I said, in the old days, in your alternator was a split ring commutator, which changed the AC from your generator to DC to recharge the battery. Sure, it would be pulse, but that's all it takes, just something to recharge the battery. Nowadays, I think they use, if I understand it right, a dual diode or something like that that does the same thing, and probably does it a little more efficiently without as much friction, without the brushes wearing out. It's more electronic. Am I right on that, Daniel, or do you know? Okay, I seem to have lost Daniel. Okay, I was hoping he would get me out of that mess. So anyway, you'll have to believe me now, because he's not here to contradict me. So there's your DC generator. Okay. Now, they had one paragraph on generators in your text. That's a little on the short side, so hopefully you filled in a little bit of the detail there. Now let's move on to, and this is also on page 163 or 6-24, that is your transformer. Now this is not those things that look like a car or an airplane and turn into some sort of robotic fighting machine. That's a toy. Okay, when we're talking transformers, I'm sitting at my um, north side window here that goes into the backyard, looking out in the backyard, and I know it's up there, but I just can't see it. I think the walnut limb is right in the way, but the transformer that changes the voltage and current from the line that goes through town to the line that comes through our house is right out there on that power pole. I just can't see the actual one now, but I know it's out there because I've been out in the backyard and seen it. Okay, every house or apartment or whatever will have, now maybe not every apartment building will have a transformer that changes the voltage and current coming off the line to go into your house. And why? Because there's problems in power transmission. Now if you think back what I said before, Edison's oh, here comes Valerie. Good that Valerie made it today. Okay, so now we have 5 people here. We have enough for a basketball team. Okay, hopefully more will be coming in. Now Valerie, I don't know if you can hear me yet, but I've already talked some to the first few people that were in class about what we'll be doing today, the week after Thanksgiving, and then final exams week. We'll go over that again when we finish the chapter lecture today. I'll go over that again. Also, I'll explain what has occurred since we last met, which has been pretty significant, at least for me. It's a rather bizarre story, but anyway, we'll get that talked about too. I think we'll have plenty of time at the end to do so. Okay, so glad you made it. I see your picture popped up. I hope you can hear me. Can you?
I can, thank you.
All right, good deal. So we're just now on page 163. We're in chapter 6, electricity. We're in section 6.5, electromagnetic induction, and we're just about to talk about transformers. We talked about electromagnetic induction in general, then how that's used in generators, and now we're going to talk about how it's used in transformers. And this is not the toy that your kids played with and it was a robot and becomes a car or a plane or something. That's a different kind of transformer. That's a toy. Okay. Why do we need transformers? Because of problems in power transmission. And we talked about earlier that originally Thomas Edison, the wizard of something or another, Menlo Street or Menlo Park or something like that, absolutely brilliant person, brilliant scientist, brilliant engineer, brilliant inventor, a rascable old character, I think. I don't think he got along with people very well. Early in his life, he became deaf in one ear and probably partially deaf in the other. I think somebody slapped him in his ear and broke his eardrum, something like that. I remember some sort of story like that. But anyway, brilliant though. But he had one big flaw in his thing. He thought AC power, electricity was dangerous and could not be used safely, and that DC was the way to go. But conducting direct current for very long in wires was not very practical. If you sent a lot of current through there, you lost a lot due to heat. Couldn't avoid it. Okay. The folks like Westinghouse, we mentioned earlier, and also Tesla were convinced AC was the way to go, alternating current. We've just described how to generate both of those, and that's the way to go. And part of the problem was right here. problems in power transmissions. Sure, if you don't have very far to go, it doesn't really matter much. But when you're trying to send a lot of current through a long distance, you got problems. Because like we talked about before in that last lab, remember, your resistance goes up the longer your wire is. Well, if you try to make the wire bigger around, then that makes it very heavy. So that's not very practical. Okay? So you have problems when you try to transmit electrical power for long distances. Well, one thing, we have lots of generators. But you know, we don't want generators right in the middle of town or in a block or somewhere like that. That could be dangerous. They could be loud. They could be smoky. They could be, yeah, you don't have electrical dam. I mean, hydroelectric dams just everywhere. You know, that's not very practical. So you have problems with power transmission. When you have high current, you have large resistive losses. If you remember, one of the formulas for power was power is equal to I squared over R, I believe it was. Okay? No, well, yeah, I think it was over R. So the larger the current, you square it, and that's how much resistance. I'm sorry, R was equal to I squared over E. That was it. Okay? Very problematic. But if you have high voltages, you have dangerous potential differences, because that's what a voltage is, a potential difference. And you really don't want that either. Okay? So the solution for that problem, to avoid large resistive line loss, heat loss, there goes all your energy, completely wasted. Oh, here comes Gerald. Okay, let me get Gerald here, and we will continue from there. So the first part of the alphabet now is coming in very strongly. Poor old Valerie's holding the bottom part of the alphabet up all by herself, and there's a couple people in the middle holding the middle up kind of too. Okay? So, and Gerald will talk a little later about how we're going to wrap up the term, and then I'll also talk a little later about what a weird week this has been for me personally, but that will come later. Okay. Um, so we're talking about transformers now. We're on in chapter 6, electricity, actually electricity and magnetism it should be, in 6.5, which is electromagnetic induction. And we talked about what that was in general already, how you generate electricity using electromagnetic induction. We finished that one, both alternating current and direct current. And now we're talking about transformers, which are used to solve the problems of power transmission. Here are the problems. When you have high currents, you have very high resistive losses of your energy. There goes all your energy being lost to heat. But a high voltage is a dangerous potential difference, so you don't want them in your homes. Okay? So what do? We use transformers. Okay? They either boost or lower both the alternating current. Now, a transformer will not work with DC, and we'll talk about why that is in a minute. It's that same idea of electromagnetic induction. Now I'm trying to see it, if I can pick it up. I can't see it. I know it's, oh, there it is. Okay. Now some people will call the box, that, I don't know if you can see that or not. Here is the power line that's plugged into the wall. Here's the line that goes to my computer. They'll call that a transformer. It's not. That's a converter. That converts AC coming from the wall to DC, which powers the computer. All computing devices and things like this use DC. But when we plug them into the wall, for instance, I'll pick up another one here. I'm not charging it now, maybe I should be, but when I go to charge my phone, I do this. Well, this is plugged into the wall, that's AC, but this is DC. In this box here, you have a converter that converts AC to DC. Don't call that a transformer. It's a type of transformation, but it's a completely different type. That's not what we're talking about here. Here we're talking about boosting or lowering AC only currents and voltages. And when you do change a current, you change the voltage. When you change the voltage, you change the current. Here's the basic relationships on which transformers are designed and built. The power in equals the power out. Okay? Power in equal power out. Now, if you remember from your power that we did last time, what power is, why is this not right? There it goes. Power in equals power out. If you remember what power is, electrical power, that's voltage in times current in, that's capital I little I, is equal to voltage out times current out. That's power, electrical power is voltage times current, whether it's coming in or going out. Okay? Now, they're talking in and out here, but let me give it a different one. Voltage on the primary side, I'm sorry, that didn't come out the way I wanted it to. Okay. If your input is what they call the primary voltage, that means PV times VP times IP is equal to, if the output side is your secondary, VS times IS. Now that's a completely different set of subscripts, but it means the same thing. Okay, let's take this one and we'll get to that later. I'm sorry, I'm jumping the gun on it. Okay, what your power in and power out are, these things here, is related to the number of coils to the voltage. And here's how those relationships go. And I wish they had a better figure for it. This is a pretty picture, but it doesn't tell you much. That is the transformer that's just like, very similar to the one that's on the power pole in my back, well, it's on the alley, and I can't quite see it here because the limb is in the way, but that is what transforms the power coming from the power line to the one coming into the house. Okay, that's what the transformer does. It drops the voltage while it's increasing current. Now, the distance between the power pole and the house is not that great, so you don't have a lot of line loss there. You do have a little, but not much. The length of the wire that goes from the transformer to the previous substation, that's a lot longer. So you want that to be higher voltage, lower current. The one coming into the house, lower voltage, so you don't have dangerous voltage that drops in the house, but higher current. Okay, now what are the inside? I think they have it coming up. Let's see if they do. Here we go. Let me erase some of my scratch there, if I can, so you can see this better. I'll erase it all for right now. Okay, here's what's happening inside. Now this is a real simplistic representation of what's going in. Okay, they show here the input side. Now the input side would not be where you plugged it into the wall, but they're showing that. So let's just show that you have, in fact, we have one, or probably two or three, okay, that we plug into the wall. We have some outdoor lighting, which is low voltage lighting, okay. It plugs into the wall, into an outlet at 120 volts, okay. Now, this is the primary coil here. Notice here, I'm just going to make a guess here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Trying to represent 10 turns. 10, this is on the primary side, your N sub P is 10. Voltage coming in here is 120. Okay, now over here on the downside, the low side, you only have one coil. Okay, so V sub S, we don't know what that voltage is now, but you only have one turn here. Okay, well guess what? This is a proportion. One thing you're missing is V sub S, so let's do our cross multiplication. 10 V sub S is equal to 1 times 120. So what we do, divide both sides by 10. Here the 10s go out, and your voltage on the secondary side is equal to, basically you just divide by 10, you lose the zeros, 12 volts. That's how you get 12 volts on the downside. Okay? That's a step down transformer. You're dropping your voltage from 120 on the input side, on the primary side, to 12 on the secondary side. All right. Now, why would you do that? Low voltage lighting. You don't want that to be a big potential difference. So if you get nicked or something like that, you have a large potential difference and you get a very serious shock. Yeah, with 12 volts you get a little shock, but not too much. Okay. I don't know if any of you auto mechanics or people who've worked with autos have gotten shocked by your electrical system in the car, but that's basically a 12 volt system because the battery is somewhere pretty close to 12 volts. Now, but the difference here, this is not DC. This is not a battery, okay? This is alternating current. Now, why does it have to be alternating current? What we said about electromagnetic induction. What induces, I'm sorry, there's something screwing up here. Let me move it. Okay. What changes the magnetic field in this is an iron core. This is like an electromagnet, only the trouble is it's going the other way. Okay? The changing electric field in this alternating current, because the current and the voltage is alternating 60 times a second. That's a changing electric field, big time. Okay? It's going positive, negative, positive, negative, positive, negative 60 times a second. That is a lot of change of an electric field. That induces a magnetic field in your core. And then that changing magnetic field, and that's always changing. Okay, here comes Rodrigo. So we got 2/3 of our automotive guys in. Let me get Rodrigo here. Now the middle part of the alphabet is coming in strong. Poor old Valerie's holding up the bottom end all by herself. The top part's got 3 people, the middle part's got 3 people, and poor old Valerie's there by herself. Sorry. Okay. So basically what you have is then with a changing electric field that's changing 60 times a second, okay, with quite a few coils here, that's changing the magnetic field in this core just as frequently, and that changing magnetic field then creates a current in this side, which is an alternating current as well. That's why these are not DC. These are alternating on this side, alternating on this side. And that drops it to 12 volts, but increases the current. We'll get to that part later. Okay? If, however, you only had one coil on this side, and you had 120 volts, that is going to create a changing magnetic field in your core, and that changing magnetic field going through that 10 turns here. Now you have, we'll change all our numbers around. Well, let's just erase them. Well, wait, I can't do it there for For some reason my pad was interfering, so I put it up out of the way. Where, oh where are you, pen? I can't see you anywhere. Can anyone see the red dot showing up on the screen? My pen is not working. Well, that's because I was using the wrong end of the pen. Ah, there we go. Okay, let's erase all that. Okay, now on the primary side, you have 120 volts coming in. You only have one turn on this side. That's divided by 1. Over here on the secondary side, you're producing a V sub S, but we don't know what it is. And here comes Rucker. Now we got all three of our auto guys here. Okay, so let me get Rucker here. All right. Now the top part is moved ahead. They've got 4 people here, middle part 3, and poor old Valerie's holding up the bottom end by herself. Okay. The number of turns on the bottom side, though, is 10 turns. On the secondary side, 10 turns. Okay. And again, this being a proportion here, 2 ratios equal each other, that's a proportion. We now do our cross multiplying here, and we have, well, let's see, we'll do it this way first. 1 times Vs is just Vs, is equal to 120 times 10, that's 1,200 volts. That's a step up transformer because you've increased the voltage from 120 on one end to 1200 on the other end, and that's where they get this number here. That's what a transformer does. The number of coils relates to the voltage. The higher the voltage, the higher number of coils, the higher the voltage, the lower number of coils, the lower the voltage. That's a direct relationship. Okay. Now, they are skipping the practical application of that, and I don't have a lot of room to write. That looks like all I've got. I can go to a whiteboard if you think that would make more sense. Are you okay with it? Let's look at equation example 6.9 on page 164. A step-up transformer has 5 loops in the primary side. So that would be, if I can get my pen to show up somewhere here, there it is. Okay. N sub P is equal to 5. Number of loops, 5 in the primary side. 20 loops on the secondary coil. So N sub S is 20 loops. Okay? If the primary coil is supplied with an alternating current, it better be, direct current will not work, of 120 volts, and that's the primary coil, so that V sub P is equal to 120 volts. What is the voltage on the secondary coil? So we're looking for V sub S. That's the unknown here. Okay, if we use this formula, but guess what, team? It doesn't have to be written this way. It could be written in any way that just keeps the relative thing of voltage to voltage on top or bottom, number of turns to number of turns on top or bottom, primary on one side, secondary on the other. That could work. So we could use this just as it's written here, put our equal sign here. That works because you have number to number, primary to primary, voltage to voltage, secondary to secondary. Everything's lined up perfectly. So let's do our cross multiplication. 5Vs is equal to multiply 20 by 120, that's 2400. Divide both sides by 5, and that would be 5 will go into 24 times, 5 will go into 48 times, and 5 will go into 0 times. 480 volts on the secondary side. Okay, the other way to look at that, this was 4 times as many turns on the secondary side as it was on the primary side, so you can multiply your 120 by 4 and you get 480. Same type thing, the math's the same. I just find solving a proportion is usually a little easier. Cross multiply. Okay, and let's see what they got. 480 volts. Okay, now what they give you here, and this is where I jumped the gun on it, they also give you this. From down here, power in equal power out. If the power in is the primary side, that's your voltage in, primary side, times the current in, that's on the primary side, equals the voltage out, that's on the secondary side, times the current out, and that's also on the secondary side. So that's equation 6.9 in your text. This one down here was 6.8 in your text. These are both on page 164. So let's pick up with 610, example 610, also on page 184, just before the bottom of the page. The step-up transformer that we just described here in example 6.9 is supplied with an alternating current at 120 volts. So we already have that. The voltage here was 120 volts. Okay, so that's going to be here. So 120 volts, okay, and a current of 10 amps. Okay, so that's your primary current. Okay, so that's going to be times 10.0 amps. Okay, and according to this thing here, what is the current flow in the secondary circuit? Well, we already know the V sub S here is 480 volts, and then we can calculate what your I sub S is, which is the current in the secondary circuit. That's what we're looking for. All right, now this time we multiply 10 times 120. If I could get my pen to show back up here, there it is. That would be 1,200 is equal to 480 times I sub S. Okay, divide both sides by 480. Okay, now the zeros cancel out, and I guess let's just use our calculators. They're easier than me explaining how to do it otherwise. I had a missed call. I don't know when that was. 3 hours ago? Maybe while I was at lunch. Okay, need to plug this phone back in. Okay, there's my calculator, and we'll do 120, because I canceled out a 0, divided by 48. Now your calculator will take care of that if you want to leave them in there. That gave me a current, the secondary current of, if I could get my pen to show up, where are you, pen? Okay, I can't find the pen. There we go, here it is. Okay, I sub S is equal to 2.5 amps. So you had, what was it? They told us 10 amps going in, which is a lot of amps, and you had 2.5 coming out. Now, do we need another digit there? Let's see what they do. No, they use 2.5 amps coming out. And here's why. Because this 120 here, that zero is not significant unless they put a bar over it. So it's 2 here, 3 there. This could probably only be 2 as well, so you probably only have 2 significant digits there. 2.5 amps on your secondary side. So if the voltage goes up on the secondary side, the current goes down. That was the purpose of your transformer. Okay? Because you're trying to solve that problem of either too high a current or too high voltage. Okay? So when those big old power lines, you've probably seen them driven under them. Big old things going across, maybe going from the power plant to the next biggest city or something like that. They're going long distances. You do not want high currents in that. You want as low a currents as you can get. So what do? Before they send them out on that, they step up the voltage, down the current till it's negligible current, really high voltage. That's why they put them off to themselves. They put them way up in the air. They don't want anything messing with them. Okay? And that cuts the current. But then when they get into town, you'll go through substations, and I can remember there's one at UAB. I don't know if it's still at the same place, but I know it's somewhere there where they step down the voltages so they can get it to the dorms, to the office buildings, to the labs, to everywhere else, and step down. And even then, they just step it down a little bit till they get over to the actual pole outside the building, step it down one last time. Now, how about going the other way? Those power plants, say the hydroelectric plant at Smith Lake or at Lay Lake or at Lake Martin or wherever it is that you have a power plant, hydroelectric plant, or the coal-fired or the oil-fired or the natural gas-fired or the nuclear power plant. Wherever that is, that's creating voltage. They step up the voltage there so they can transmit it for long distances to the towns which are far away from those power plants. They don't want those power plants right outside the city. They don't want that nuclear power plant right outside town. They want it as far away as they can get it, but they also need, water coolant and things like that. So anyway, that's why they use the transformers. Step up transformers to get it transmitted over long distances where you have high voltage, and then step down transformers to bring it back into town or back into your houses. Okay. So, any questions on transformers? If you step up the voltage, you're going to step down the current. Okay. All right. Now we're ready for 6.6. Oh, before we get to 6.6, there's a really interesting little blurb. It's the concepts applied. It's called swinging coils. And I have seen this, or at least a picture of this happening before. What they do, if you've got your book open, this is on page 165 or 6-26. All they have is a coil of wire swinging, hanging from some sort of support. Okay, just hanging there. Light wire that's able to swing it. But most of the time it isn't. Put under that a magnet, a strong permanent magnet, say. Okay. Then run wires over to another coil, bigger or smaller, it doesn't matter. Okay. And that's hanging over another magnet. And that's all there is. There's no power supply, there's no battery, there's nothing plugged into the wall, they're just hanging there. Okay? And they didn't just do that. They hang there until you take one and start it rocking. Okay? Start that one coil rocking over its battery, and you know what happens? The other coil starts rocking over it. They're long distance away from each other. You're not doing anything to the second one. You start the first one rocking, the second one starts rocking. You stop the first one, the second one stops. You stop the second one, yeah. Why? Because the coil of wire is your electric charges are in that wire. Your magnetic field lines are over that permanent magnet, both of the permanent magnets. And if you start that first coil rocking, you're changing the number of field lines being cut by that coil of wire. A changing field lines being cut by a coil of wire sends a current through the wire. No battery, no plug-in, it sends a current through the wire. It's a changing current because it's flipping back and forth and back and forth and back and forth. So it's a changing current. Well, a changing current in a coil of wire creates a changing magnetic field. This is magnetic induction, okay, electromagnetic induction. So that's changing your magnetic field, and that changing magnetic field over the permanent magnet starts it swinging too, because like poles repel each other, unlike poles attract each other, so it starts swinging back and forth. Completely independent, except they're connected by electrical wires. All right, so that was, if you have time to play around and do something like that, it's a fun thing to look at. All right, now we move to 6.6, and these are circuit connections. Okay? Now, as we said earlier, practically all generated electricity at your power plants, at your actually even in your car, practically all the generated electricity is AC, alternating current, because you use electromagnetic induction to generate that electricity. Okay? Now, from power plants, it's transmitted over high voltage lines. How do you get the high voltage? Step up transformers at the power plants. Step it up to very high voltage and move that with very low current, very little line loss for long distances. Then when you get into town, you step it down, and then when you get into neighborhoods, you step it down. Before you get to your home or your business, you step it down until it's something that's usable. Okay, that's your alternating current. Any plug you plug into the wall pretty much is alternating current. Okay, now what's direct current? Well, that's used in automobiles. I said, wait a minute. Didn't I just say your automobile has a generator in it producing alternating current? It does, but that alternating current first has to go through. In the older cars, it was a split ring commutator, which changed the alternating current to pulsed DC. Nowadays they use either dual diodes or one of the automotive students one year told me something else, a different name that they use. I don't know what the electronics of it is, but they use something. A diode trio, is that what you said?
Yes, sir.
Okay, and that's okay. A dual diodes is 2, a diode trio is 3, and that smooths out that pulse direct current and makes it almost even direct current. And that's what you use to recharge your battery. Okay, because that generator is producing alternating current, you've got to change that to direct current to recharge the battery and to run other things in the car as well. So this is used in automobiles, cell phones, MP3 players, laptops like I'm working on now, you may be doing now, just about everything like that. Anything that has a battery associated with it, automobiles included, has to be direct current. Okay? These things are movable and portable. That's why you don't have to be plugged into a wall somewhere. Okay? The main current source is chemical batteries unless you're charging those with something else. Okay? And the generator in your car is recharging its batteries. the plug into the wall with a converter on it. That's changing the AC to DC. That's what's keeping my computer running. Your plug at the end of your uh, telephone recharger, that's what's making that happen, your cell phone recharger. Um, you have those converters. They're sometimes called transformer. The better name is converter. AC to DC converter. Okay? But someplace or another, they probably do have chemical batteries. Now, in a hybrid car, you have a pretty hefty load of chemical batteries, and then you have lots of ways to charge those batteries. The plug-in when you go to recharge it overnight in your garage, or if you are going on a long trip. I haven't seen them, but there got to be stations out there that you can plug your cars into. But even things like regenerative braking, which rather than using friction, which has heat loss, you're basically have an electric generator there, and that's for creating the resistance to brake your car, but it's also manufacturing current to recharge your battery. Okay, so that's a pretty neat concept. And I assume that it works just as good as a mechanical uh, brake. It must. I haven't heard of that many accidents because of it. Okay, so let's look at this again. The title of this section, Current Circuit Connections, and we're going to look, and our examples here are basically going to be direct current examples, but what we're talking about here is the same stuff that we use in alternating current. There's some little subtle differences, but we're not getting into those. Okay, so if you have voltage sources in circuits and these are in series with each other, what does that mean? That means you connect battery to battery to battery by plus to minus, and ultimately plus to minus. Okay, this is just like you have in a flashlight. You always line the batteries up facing the same direction, so the positive pole of this one is hitting the negative pole of that one, the positive pole of this one's hitting the negative pole of that one, so they are in series. What are you doing when you do that? You're adding the sum of your single voltages. If this was a 1.5, that was a 1.5, that was a 1.5, you have 4.5 volts. Okay? Now, but you only have one current pathway. All the current goes through everything the same way, including the light bulb, so basically you only have one current. You're adding the amount of current that, because the voltage, if that's the same resistor, that's the same resistor here, this battery would be providing potential difference across that one would, and that one would. So you would be adding the individual currents you would get from the three batteries, but you've only got one current going through everything. Single current pathway. Now, if you hooked those batteries up plus to plus to plus, minus to minus to minus, what have you done there? Well, that's called a parallel circuit, because plus is to plus, minus to minus, and what you have done there is basically all your negative terminals are connected. This battery, if that was a 1.5, this is a 1.5, that's a 1.5. All you see here is 1.5 voltage difference. Well, what have you done? It's like you've made three bigger batteries, still 1.5 difference in voltage, but now you've increased basically the size of the battery, meaning it lasts longer. Okay, all the negative terminals are connected, all the positive terminals are connected. The resultant voltage is determined by the largest cell voltage. Now if that was a 1.5, that's a 2, and that was a 1.5, your voltage across here would be a 2. okay, because it goes with the largest battery. You don't add the voltages, but what you do get is greater electrical energy available. In other words, you have, okay, let's just say, now I don't know if they have power to the top of Mount Cheaha or not. I don't know. But let's just say Mount Cheaha, the largest, the tallest mountain in the state of Alabama, that you had the weather station up there, but there was no power going to the weather station. So you had to run it off batteries. And you didn't want to climb Mount Cheaha every few days, weeks, or months or something like that to change batteries. You put as many batteries as you can in parallel because you don't want to change the voltage going to the equipment, but you want to make it last longer. And then maybe you only have to go once or twice a year to go up to Mount Cheaha and change the batteries. Then you would put your batteries in parallel as opposed to series. The series makes that light brighter. The parallel, you got the same brightness of the light because there's same resistance, same voltage across here. So all you do is make that light last longer. Okay? More electrical energy available. That's if you connect your batteries either in series or in parallel. Now, that really doesn't make a lot of sense when you're talking DC, so this is mostly, AC, that's mostly a DC concept. Okay. But this is the part that makes you could have either AC or DC here. And these are if you have one power supply, whatever that is. They're showing a battery here that could be the plug in the wall. Okay, that's just providing a voltage difference. Okay, 1.5 volts, 5 volt, 9 volts, 120 volts, whatever this is. Okay, now for some reason here they show electron current. Most of the time we use what we call conventional current, which goes from high potential to low potential. They're showing electron. Guess what? It doesn't matter at all which way this current's running. It's all going to act the same. Okay, so you have a potential difference here, whether it's from a battery or a plug in the wall, and you have these three resistances up here. But guess what? There's only one pathway. This is what we call a series connection. Only one pathway. Okay? Well, the same current goes through all three lamps, all three lights, and you only got one voltage source here. So you sum up your resistors, R1 plus R2 plus R3, and use that total resistance to calculate how much current you get. You know the voltage, you know the resistances, you calculate the current. Now, there's a current drop across this lamp, a different one across this one, and a different one across this one. The total current drop has to equal the voltage drop, not a current drop. Same current goes through all of it. The voltage drop across this one plus the voltage drop across this one plus the voltage drop across this one has to equal the voltage supplied by your battery. That's all you got, okay? And if this was a plug in the wall, that would be 120, okay? So whatever you've got here, the more things you have in series, then the more your resistance is. The current drops as more elements are added, okay? Because you've got the same voltage, greater resistance, so your current has to plummet, okay? All right, here is the formula that represents that. Your total resistance in a series circuit, you add the resistor together, R1 plus R2 plus R3 plus as many resistors as you put there. The more you put there, the greater your total resistance is. The greater your total resistance here, with the same voltage source, your current has to drop. So the current drops as more resistors are added to the circuit. Okay? Now, in a parallel connection, you have more than one current pathway available. And this is what that would represent. Here is a battery, or a voltage supply, somehow you got it down here, plus on this side, minus on this side. It doesn't matter which way the current's going, okay? Now, your voltage drop across that light is the same as the voltage drop across here, same as the voltage drop across here, because they each have their own pathway to get back to the battery. So whatever the voltage drop is here, same across each light bulb. Oh, wait a minute, how can that be? Well, that means the battery has to supply more current to supply this one and that one and that one. So you see your currents split. Back here, the current was the same in all of them. Your voltage drops, where did it go? Okay, the voltage drops added, but the current was the same. The voltage was the same, but the voltage drop across each added, meaning the resistors added. Okay, over here, the voltage drop, the voltage is the same, sort of like the current was the same before, so your current split. You send some current to this one, some current to that one, some current to that one. Man, what are you doing? You're draining your battery like crazy. The more things you put in parallel, the quicker you use up the battery. Now, I just heard a noise. I don't know what it was. Is someone trying to get in the room? No, we have 8 students here. Let me make sure I've got 8 on my books. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Not a huge show for today, but hopefully more will be coming in. Okay? Goodness, my hands are getting cold. The sun's going down. It's chilling off some. Okay. So with a parallel connection, more than one current path is available, so you have to add your currents together, not one current going through everything. You add the currents. The currents are determined by the resistance of the individual circuit and your voltage supply. So overall resistance, and this sounds crazy, your overall resistance drops as more elements are added. Hey, that doesn't make any sense, does it? Yes, it does. Because you're making the battery provide more current because you add another light bulb here. Now the same voltage here now has to supply more current to the whole system. Well, same voltage, more current, that means the overall resistance has to go down. So the more things you add on the same circuit, the greater your current draw is, the less your overall resistance is. Every one of those has a resistance, but the effective resistance drops. Now, how can that be? Okay, the total current increases the more elements are added. With the same voltage here, whether that's plugging into the wall or a battery, then the lower the resistance of the overall circuit is, because with the same voltage you got more current, so your overall resistance must be less. Sounds strange, but it's true. Here's the formula that works for that. If I can get it to come up. Oh, I have to click on the slide again and see if, what in the world is going on? There it goes. Okay. Your total 1 over the total resistance is equal 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4, as many as you got here. Okay, so when you take a reciprocal, the bigger the resistance, the smaller that fraction is. But you're still adding it to another fraction to another fraction. So it seems to be adding. So that would make the 1 over R total get bigger. But because that's a reciprocal relationship, inverse relationship, that makes the R total go down. And that's what's happening with resistances in parallel circuits. Okay? So, sounds bizarre, but it's true. Okay? before we get to household currents, let's do, and I should have broken, in fact, I think I'll go back to series. Okay. Okay. I should have done this then. But before we do, on page 166, I should have shown that. The trouble is I can't see my camera picture now, so I don't know where to hold this. But if you got your book, this is at it looks like a hydroelectric power plant, and those, I bet you, are step-up transformers that take that whatever voltage you're producing at the power plant, stepping it up to make very large voltage before they send it out across the wires. This then is the step down transformer, which we saw earlier, and that's the one that happens on your power pole outside your house, your apartment, your business, or whatever, and steps down that. There's a Science and Society there. Blackout reveals pollution. It's sort of an interesting thing, but I don't really, I mean, it's interesting. Read it. It has some questions. If you want to write a paper on that, you certainly can. Okay, all that done, let's do example 611, which is based on series. Okay, so 3 resistors with resistances of 12 ohms, 8 ohms, and 24 ohms are in a series circuit with a 12 volt battery. Series circuit with a 12 volt battery. Now I'm going to draw that for you here. Now my picture won't be very pretty, but this is sort of how you draw it. Okay, now basically we don't usually run them like this, but they could. This is what the problem is. So let's draw our 12 volt battery here. I'll draw it this way. Now I'm going to do it this way. This is a good way to draw a battery. Okay. Okay. And you run into a 1 resistor here, 1 resistor there, 1 resistor there, and then it comes back to the battery. Now, what this is representing here, and I know you guys who deal with automobiles, you know that inside your battery you have parallel plates. And if I'm not mistaken, they used to be lead plates alternating with lead sulfate plates, it seems like, or something like that. And the sulfuric acid was added to the battery, and that provided the electrolyte. Well, it doesn't really matter. And usually you had 6 of those. I didn't want to draw that many. Usually the longer plate here is the positive side, the shorter plate here is the negative side. So basically this is like your 3 batteries in series 2, but we're not dealing with that now. Basically each of those 6 pairs of plates was about a 2 volt potential difference, so that's where you get your 12 volt battery. A lot of times new it would be a little bit more than 12 volts. Okay, now so there's your 12 volt battery. I didn't draw 6 plates, I only draw 3 pairs of plates. This was your 12 ohm resistor, so we'll call that R1 is 12 ohms, and the symbol for ohm is a capital omega from the Greek alphabet. This R2 was an 8 ohm resistor, and R3 was a 24 ohm resistor. Okay. In series with a 12 volt battery. In series means there's only one current pathway here. Okay? Now, what is it? The A question, what is the total resistance of the resistors? Okay? Since these are in series with each other, you just add the resistors. So the total resistor, sometimes they call it R sub T for total. Sometimes they call it R sub E for effective. I like R sub E better, but I think they're calling it R sub T. R sub T would be R1 plus R2 plus R3, which would be 12 ohms plus 8 ohms plus 24 ohms. Okay, 12 and 8 is 20, and another 24 would be 44 ohms would be your total resistance. That's a fair amount of resistance. Well, not really, but it's just okay. How much current can move through the circuit? That's the B part. Well, you know, this is the total voltage here is 12 volts. They told you that. I don't think they put a 0.0 after it, did they? No, they just says 12 volts. Okay, your total resistor is 44. Well, from Ohm's law, I is equal to V over R, which would be 12 volts divided by 44 ohms. And now I'm going to have to pull up my calculator for that one. I could reduce it to a certain amount, but basically I'd still need my calculator. 12 volts. By the way, folks, the lab today is going to be a lot like this, so get to know it. 12 volts divided by 44 ohms equal 0.27 amps. Okay, if I could get my pen, approximately 0.27 amps. Okay, now you could call that 272 milliamps or 273 milliamps if you wanted to. Okay, let's see what the book got. 0.27 amps. Yeah, very good. Now, what is the current through each resistor? Well, guess what? There is only one pathway for the current. If I could get my pen to show up somewhere here, get out of there. Okay, here we go. This is, I draw conventional current. The book sometimes draws electron. There's only one current, so it's the same current across each resistor. Okay, and that would be 0.27. No, I'm sorry. Look at that. Y'all let me get away with that? What is wrong with you? You're not keeping me straight here. Okay, you're letting me wonder. That's 0.27 amps. I think I said amps and wrote ohms. Okay, that goes through every resistor. Well, let's see what happens with that. If we have that 0.27272727, and because I times R is equal to V, let's multiply that by 12 ohms plus 0.27 times 8 ohms plus 0.27 times 24 ohms equal, and you almost get 12 volts. The reason we don't, this was a round off. You rounded from 0.2727272727 to 0.27, so that's a rounding downward. So sure enough, you get an answer that's a little too less. But if you round that to two significant digits, it does round up to 12 volts. So yeah, that's what you get. You get a different voltage drop across each resistor because you got the same current through them but different resistances, and that adds back up to the same voltage increase that your battery supplied. Okay, so what's the current through each resistor? Same thing, 0.27 ohms. Okay, now, sorry about this. I skipped some things here. I'll try to make it up for you now. I'm going to recharge, put my phone back on charge again. This is an older phone and sometimes it tends to lose charge a bit too quickly. I'm also going to get a drink of water. Okay, now before we get to the parallel circuit, there's a closer look, and this is at solar cells. Okay, And I think we talked a little bit more about this before, but you certainly can look at this. Solar cells produce DC current. Okay? They can't produce alternating. There's nothing moving in them. It's DC current. So, on the scientific calculators, most of the time, this is a telephone, it's not one, they have a bank of little solar cells at the top, and as long as you operate them in the light, they keep themselves charged. You don't need them plugged into the wall. Now, the high-powered fancy graphing calculators, they take too much current than can be produced that way, so they run down their batteries. But most of your scientific calculators run off solar cells. And even doesn't have to be sunlight, it could be the light from a incandescent bulb, a compact fluorescent, a LED. It doesn't matter what kind of light, it runs off light. And those are called solar cells. So there's a good little blurb there on that, and that shows an example of one out in the middle of nowhere where you don't have much power, but it looks like a fairly dry area, so you would have a lot of sunlight probably. They run their call box on solar cells, and they probably have some pretty good batteries in there, and that keeps it going even at night or rainy days or things like that. I don't know if any of you are familiar with the bike service they have in the city of Birmingham. I can't think what they're called, but they're all green bikes, and the stations where you park them, if you've ever noticed, has a big bank of solar cells on top, all facing the south, so they get the maximum sun light hitting them. And some of those bikes actually do have battery assist, not a lot, but a little bit. So when you're going up hills and you're, say, anemic like I am or something and need a little help, you can use the electric motors in them to help you get up the hills. Now, I've never used those bikes. I would be really stubborn and try to pedal my way all the way through, but you know, older people or people who have other issues. Now, they give you a little bit of diagram there. They talk about the PN junctions. It's pretty interesting stuff. Okay, the P is the positive side, the N is the negative side, and they basically are moving charges across the junction, and that's what creates the potential difference that they use to charge batteries. All right, it's a really good potential paper topic if you want to follow up on that. But this cannot be your source. You have to get the source from outside the book. This can give you the idea about it. Okay, so let's move on to example 612. And 612 came about after we did parallel. So let's use this blank space here. Assume that the three resistances in example 611 are now connected in parallel. So I'm going to draw the battery down here similar to what I did before. Long, short, long, short, long, short. Okay. And then I'm going to run up here and hit one resistor here. Whoa, that should come in there. Okay. And hit another resistor up here. And hit another resistor somewhere up here. Okay. Again, this is a 12 volt battery. And let's see, what were they? One of them was 8 ohms, I believe it was. This was 12 ohms, I believe it was. And this was 24 ohms. This we called R3, not that it mattered. This we called R2, not that it mattered. And this we called R1. That's just so we could talk about them individually. Okay? Now, that setup, the question is, now connected in parallel, what is the combined resistance? Now this one I like to call effective resistance because it doesn't sound like a total. And I'm trying to find my pen, and oh, there it is. Okay, and this one we use the reciprocal relationship, 1 over RE. I think the book uses something else. They call it total still. I'm going to call it effective resistance. Is equal to, if I can now find my pen again, there it is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay, now, oh boy, I'm running out of energy. I apologize for this. I don't know if we got as many here as we're going to get here, but maybe I'll go on and tell my story. This week has been really strange, especially the 2 days since we met last. Now this is too long of a story. I hate to take class time for it, but I do want to explain what's happening. I think I've told y'all before I have a mild form of leukemia. Okay, it's called chronic lymphocytic leukemia. That means, what it means is my white cell count, certain white cells start multiplying really fast sometimes, and they're the malignant cells, and they reproduce too fast, and they get out of control. Well, the last time I had a treatment before this term was back in January, early January. Now, I've had this disease, it's been diagnosed since 1991. Now, that was before many of you were born, okay? So I've had it awfully, more than 29 years now, okay? It's not that bad, okay? It's never really affected me very negatively, except for having to have treatments, okay? It's one they say, well, so far we can't cure it, but we can treat it. And so far they've been doing a good job of that. So it was diagnosed back in 91, and it was 17 years before I needed my first treatment, okay? The counts just slowly kept going up, slowly kept going up, slowly kept going up. So for 17 years, we just monitored the counts and made sure they weren't messing with anything else. And I was lucky, they went up really slowly. Well, then 17 years in, they were getting so high, really, really high, they decided to treat me with 2 chemicals, okay? And those were sort of harsh chemicals, not super harsh, not as harsh as what, say, breast cancer or things like this, but they were pretty hard. I mean, they didn't make any hair fall out, believe it or not. They just made me feel a little sick. I'd have 3 days in a row with the treatments. By the 3rd day, I was wanting to throw up a lot. Okay. First 2 days, I sat there and graded papers, while I was getting the treatment. The 3rd day, I didn't feel like doing anything. And if I didn't take my compazine, which has settled your stomach, on time, I would usually lose lunch. Okay. And then I felt pretty lousy for most of the weekend, but then I was back teaching on Monday. I had the treatments on Wednesday, Thursday, Friday, and then back teaching on Monday. Usually even went to church on Sunday if I felt like it. Okay. Now, but anyway, that was 17 years into the disease. Well, after that, we started using what they call monoclonal antibodies. I didn't need those harsh chemicals anymore. They had developed these monoclonal antibodies. Actually, I changed doctors. The old doctor retired. He didn't like the monoclonal antibodies. The new one loved them, so he started me on those. And so far, I've never gone back to the chemicals. Always been monoclonal antibodies, which, yeah, I'm sure is a chemical too, but it's not anything like the other. Okay. So anyway, I went through 2 of those. They were okay, fairly effective, and then after a while lost the effectiveness. So I'm on my 3rd one now, and I had a treatment of that, and I've had them before, but I had the treatment of that back in January. And the counts were pretty high when I had the treatment. I don't remember how high, 50,000, something like that. Should have been maximum 11,000, so pretty high. Well, I went back in 3 months for him to evaluate it, and 3 months later it was 4,000. So 3 months, the treatment had knocked down the white cell counts from, say, 50,000 to way less than 4,000, and then in 3 months it had climbed back up to basically just over 4,000. Well, the range they want you to be is between 4,000 and 11,000. So we were happy with that, no treatment. This was last March or sometime around there. Sometime around June or so, I went back for another evaluation, and by that time the counts had gone up to 18,000. Well, that's above what they want it to be, but it wasn't that far above. So, and that was back when everybody was really, really, really worried about COVID because things were getting spiking, going out of control. And he said, let's just let it sit because if you mess with the white cells, you're messing with your resistance. Let's let it rest. I was okay with that. So 3 more months went by. This would have made it about September or early October, sometime in there. And we went by for another evaluation. It had jumped from 18 to 19,000 up to 140,000, 130,000, something like that. Way out of control. Okay. Was that just a comment or did you have something to say?
Oh no, I was
Yeah.
saying, wow.
Wow. Yeah, exactly. That's what the doctor said too. So you need a treatment. Okay. And if you remember about 4 weeks ago today, 4 weeks ago today, I had a treatment. And because the counts were so high, they wanted me to do 10% the first day and 90% the second day. And that was a day that I had to cancel my first 3 classes because that's when I had the 10% treatment. But I made it back just in time for this class. Okay? I don't know if y'all remember that, but that was about 4 weeks ago today, in fact. So,
Yeah, I remember. We remember that.
okay. So, in that first day when I had the 10% treatment, I could tell there was a war going on inside. I mean, I got hot. I knew that the battle was raging in there, okay? So I asked for crushed ice to be eating on. I ate on crushed ice for about 2 hours until finally things settled down, and that's why I was able to get back here and teach the class. Okay, now the next day I had 90% treatment, and I thought, boy, what's this going to be like? But it was, I could tell stuff was going on, but I never got all that uncomfortable. I did eat some ice, but it wasn't because I really needed to. I like to chew on ice. So it wasn't a bad day at all. It took longer to do the treatment because it was 90% treatment, not 10%. But right before I took that treatment on Thursday, and then certainly after that treatment on Friday, I was way tired. My stamina went way down. I could sometimes hear my heartbeat when I did anything. Even laying in bed, I could hear my heart beating, and normally I can't. So I knew I had something going on. I knew before the treatment, my the white cells, all that many white cells, had crowded out the red, so I was anemic. I think I told you all that before. So after the treatment, the anemia got worse. I could tell it was worse. They didn't do any blood work to verify that, but I could tell I was exhausted. Okay, so fast forward, not that my story is very fast, but let's go forward about 4 weeks. Okay, I was scheduled for another treatment tomorrow. Okay, they weren't going to do 2 days, just one day. I knew I did not want a treatment tomorrow. I was still feeling so exhausted. I knew I was still very anemic. So last Sunday evening, emailed or went through the portal there they have at UAB and said, can I have my blood work done on Wednesday rather than waiting till the treatment day on Friday? And they didn't respond on Monday. And finally on Tuesday afternoon after this class, something like 5:45 they responded. I didn't see it until later. I saw they said, yes, you can have treatment anytime between now and Friday. So Wednesday and Friday. Well, I had free time on for Wednesday morning. I don't have class until 10. So I went to have my blood work done on Wednesday. I tried to get there early and got it done. Was coming back. I thought I heard my phone felt my phone vibrate, but I was driving, so I didn't want to mess with it. I came back. I didn't think of looking at the phone, and then when I finally checked it, there were 3 messages from the nurse. The treatment had taken the counts from 140,000 almost 4 weeks later to 1.4 thousand. Okay, that treatment did a number and a half on those counts, but it also made me severely anemic. So anemic, they said you need to come in Thursday, they were saying tomorrow or Friday, and get a blood transfusion. You're not having a treatment. I knew I didn't need a treatment, but they said you do need blood transfusion because my red cells were so low, and that's why I was so exhausted all the time. And my platelets were critically low, are critically low, and the neutrophils, which they use that's what battles diseases, they were way critically low too. So rather than having a treatment tomorrow, I'm having a transfusion tomorrow. I've never had one in my life. I've had infusions, but not transfusions. So they're going to give me blood tomorrow, and they're going to give me a shot to boost my immune system. So I will be out of pocket tomorrow. No, not available during office hours. Now, supposedly the transfusion may take as little as 2 hours. And if that's the case, I'm supposed to feel way better basically immediately. So I may be able to come home and have some office hours from 10 till 12 or something like that. So I'm hoping.
You're going to be very hungry. You're going to find yourself very hungry after the transfusion as well.
Is that right? It sounds like the
Oh, yes.
voice of experience there, huh? Okay.
Yes.
Okay.
Lots of energy.
Okay, well, that's good to know. I'm always hungry though, so I don't know what that's going to be like. Okay, but hopefully I'll be metabolizing a lot better than I am now. I couldn't figure out why I'm eating no more or less than what I used to eat, but I'm gaining weight, and that's because I'm not metabolizing because I don't have enough red cells to do that. So anyway, that's the story tomorrow. I hope I don't have anyone signed up to virtual advise tomorrow because I'll be in the clinic and I probably won't be able to get a signal to do that, but I'll worry about that tomorrow. Okay, so all this came from the fact I said I'm running out of gas now. I get really tired toward the end of the day, so I'm going to stop right now and take a sip of Coke. I don't know if it's good for me or not. It probably isn't, but it boosts a little bit of energy. I hate to do this in class, but I feel like I need it. So anyway, here I go. We've set this up. We haven't done the math on it yet. Let's do the math. I was also getting a pretty bad headache, so hopefully that'll help that too. Where is my pen? There you are. Okay. So this is 1 over 8 plus 1 over, I'm leaving off the units because I don't have enough room to write, 1 over 12 plus 1 over 24. Now I'm going to show you how to do this on your calculator. It would make it a lot faster, but let's do this the old-fashioned way now. And that old-fashioned way is find your least common denominator. Least common denominator is 24 because 8 goes into 24, 12 goes into 24, and of course 24 goes into 24. Okay, so 8 will go into 24 3 times, so that would be 3 24ths for that one, plus 2 24ths for this one. 12 will go into 24 2 times. 2 times 1 is 2. And, of course, this is just 1/24 here. So that gives you 6 over 24. They set it up so it'd be really easy. Well, that reduces to 1 over 4. But that's 1 over your effective resistance. So that means your effective resistance here, believe it or not, the effective resistance here, which I think the book calls the total resistance, that is 4 ohms. I'll put my units back in there. Look at that. the effective resistance is less than any one of the resistances, and that's always going to be the case for parallel circuits. Okay? Now, let me show you how to do that on a calculator. Now, I've got a cell phone, which is not a great calculator, but it functions that way. So I'm going to turn it on again. Get to calculator mode. Okay. Turn it sideways. I can't see where my camera is now. Turn it sideways so it goes to scientific calculator mode. Now, somewhere on that calculator, you'll find a key that on this phone, it's a, where is my pen? There it is. 1 over X key. That means it's a reciprocal key. On some calculators, it may be X to the minus 1 key. Those mean the same things. Either one of those keys. Okay? So what you do, and this is the easy way to do it. Okay? Now that was the easy problem because they all worked out evenly. You type in 8 and then press the 1 over X key. Plus 12, 1 over X key, plus 24, 1 over X key, equals, and that gives you a sum, and then you press 1 over X. And it gives you the wrong answer. Okay, I must have typed in something wrong, or else. No, 4 ohms is the answer. Let me try that again. I must have pressed something wrong. Okay. 8, 1 over X, plus 12. I don't think the 2 hit. 1 over X, plus 24. I've got fat fingers and little keys. 1 over X, equal. And yeah, this is working out right. Then press 1 over X one more time and you get 4. Okay. And that's your answer. Okay. Now, I'm going to plug the phone back in so it can charge while I'm doing some more talking, but I'll probably pull it back out in just a few minutes. Okay. Now, that answers the first question. They say, what is the combined resistance, which I call the effective resistance, and that's 4 ohms. Okay. The second one question says, what is the current in the overall circuit? The current in the overall circuit. That means the current that leaves the battery here and comes back in here. Okay. What is that current? I. I'm going to call that IT because that is a total current. Okay. Well, that would be your I, just like before, is equal to V over R. But notice you have a very different R this time. That would be 12 volts divided by 4 ohms. That's your effective resistance now. So I'm going to call that R sub E here. And the capital E there, little e here. So what's that? 3 amps. There is your total current. Okay? But then the C question says, what is the current through each resistor? Well, wait a minute. This, remember, is a 12 volt. Where is my pen? There it is. You have 12 volts across here, which means it's the same 12 volts across here, which is the same 12 volts across here, which is the same 12 volts across here. So guess what? How do you get voltage knowing resistance? Current, knowing voltage and resistance? I1. Now, this total current here, 3 amps, part of it turns this way, and we'll call that I1. Part of it comes on up here and becomes I2, and part of it comes all the way up here and becomes I3. Remember, your current splits in a parallel circuit. So I1 is going to be V divided by R1. So that would be 12 volts divided by 8 ohms. Okay, I think I can do that one in my head. 8 will go into 12 one time with 4 left over, and 4/8 is 1.5 amps. Okay, let's do I2. I2 is equal to V, 12 volts, divided by 12 ohms. Hey, I can do that one in my head too. Okay, I can't write ohms, but I can do that in my head. And that would be 1 amp. And then up here for I3, I'm running out of room down there, so let's do it up here. I3 is equal to 12 volts divided by 24 ohms. And 12 divided by 24 is 0.5 amps. And if you add 0.5 to 1.5, that gives you 2. Add one more, you got 3. There's your total current, 3 amps. So yeah, this makes perfect sense. In a series circuit, same current goes through everything. Add your resistors, divide that into your voltage, you get your current. Same current goes through all. You have different voltage drops across each resistor, but you have the same current through them all. With a parallel circuit, you have the same voltage across each resistor, meaning your currents change as you go through there. The more resistors you add, the more current that poor old battery has to supply, and in supplying more current, the overall effective resistance of that circuit goes down, and you run your battery down way faster. Okay, now, okay, we'll talk about the next part later. So anyway, we got 1 amp, 1.5 amp, and 0.5 amp. So we got the same one. They numbered the resistances differently. I don't know why, okay, but they got the same answers. All right, any questions on resistances in circuits? Okay, there was the formula we used. We had 3 of them. I showed you how to use the calculator too. All right, now I think it's the last section in the text, and that's household circuits. How are we doing on time? I think we're going to work this up right well timed here. What we have here is a combination of series and parallel circuitry. Okay. Now, if we were in the classroom, which we're not, okay, I would look up and say, look overhead. How are those resistors, those lights, those fluorescent tubes out there, how are they connected? They are connected in parallel. Okay? The light fixtures in a room are in parallel. I can't say that here. We only got one light. Okay? And yeah, whatever. Okay, so the light fixtures are in parallel. However, the switch over there by the door, that one is in series with all those lights, because if it was parallel, you could turn it on or off and there'd be other circuits there. So the switch has to be in series with everything that's in its circuit, but the things in the circuit then can be in parallel. Okay, so the light fixtures in a room are in parallel. Most of the time your appliances are in parallel. How do you know that? Because if you have them all plugged into the wall, guess what? If you unplug one, the others stay on. Well, let's go back and look at our light bulbs here. If you unscrew this light bulb, these two stay on, okay? Because they each have a pathway. But let's go back here. And if you take one of these out, you've broken the pathway. They all go out because you only have one circuit that goes through the whole thing. You take out a bulb, you break the circuit. There's no way for it to get from here to there. Okay, so they all go out. Okay, so therefore in your home, everything you plug into the wall, you want to work, whether anything else is plugged in on the same circuit or not. Okay? So the same, okay, light fixtures in the room, appliances are in parallel. The same voltage is available to them all because they're parallel. Okay? Now, your circuit breakers and your fuses and your switches have to be in series with everything they're controlling. Okay, so if this is your switch that's controlling only that light bulb, it's got to be in series with that light bulb. But that light bulb, when the switch is on or off, is parallel with all your outlets here. However, your circuit breaker, if all this is on one circuit, then this is the load wire, which is bringing in the energy here, goes through the circuit breakers and comes back out. And guess what, team? If you put too many things on that same circuit, let's say you plug in another high, say a space heater here, and maybe one there, and maybe your refrigerator there that has a big compressor on it, and maybe you plug in your coffee pot here, and that's going to use a lot of heat. And over here you plug in no, say another space heater, okay, or something like that. You get all those on a parallel circuit. Everything you plug in, the more resistance it has, it drives down the overall resistance, meaning that poor old power source that you have is having to provide more and more and more current to feed all those things. Well, guess what? If you exceed the current that circuit breaker is rated as, it's going to flip. Okay? Now, let me tell you a little dumb story. We are almost out of time, but I think I can do this. The first house that my wife and I moved into when we moved here to Birmingham, we were renting from a nice little lady who lived next door. And this was a big old, pretty old house. It was a leaky old house, though. I mean, some places in the basement you could look through and see outside. We didn't heat the basement, but there was still plenty of leakage between the basement and the main floors. And they said the kitchen has been electrically renovated, and it did have outlets all around the kitchen. Okay, which was nice. My wife liked to cook. She liked to drink coffee, so she had coffee maker. She ground her own beans back then. So she had her the bean grinder in there. We had a microwave in there. We had, of course, a refrigerator. I believe the stove and the oven were both electric, so they were in there. Everything was plugged in. Plenty of outlets to plug into. Now, in all the other rooms in the house, there was generally one outlet. Okay, just one outlet. So we had to run extension cords to feed the lamps and the radios and the television and things like this. So it was sort of awkward, but okay. Except for the fact when they rewired the kitchen, they only had one circuit. And this was an old house. Like I said, it has a fuse box, not circuit breakers. Well, we lived in walking distance of what used to be the Big B. It was a drugstore chain, and we kept them in business with fuses. Because if my wife was turned on the coffee maker, which used a lot of current, and then maybe had something going on the stove or something like that, if then the refrigerator compressor happened to kick in at the same time, there went the fuse. Everything went out. So we just had to keep a supply of fuses there because we never knew when that refrigerator was going to kick on the compressor. And we were using fuses like crazy. So we tried to make it so we didn't run the microwave at the same time as the toaster oven or the same time as the coffee maker and stuff. We did everything we could not to have two things on at once, but if we had something on, especially something that drew a lot, and that compressor came on the refrigerator, which we couldn't control, there went the fuse. And you don't reuse a fuse, you have to get a new one. Circuit breakers, you can just trip them and get them to work again. So we learned the circuitry really nicely. Okay, so here are a few things about circuit safety. Now they have one thing showing here, they really should show two. What we have is a potential difference from 2 wires per device. Okay, now believe it or not, the load carrier is the small one. The big fat one is the ground. Okay, because this is what we call AC circuit that's plugged into the wall. So one of these is your load carrier that's bringing in the hot wire, they call it, and the other is your grounded or neutral wire. Now this is a two-prong plug, but it's called a polarized plug. You have to plug this one into the source, this one into the ground. And you see on your receptacle there, you have a bigger side and a smaller side. You can't flip those over, it won't work. Okay, now the room I'm in right here only has two prong plugs in it. To do my computer, I have to run an extension cord from the bathroom, which had a ground fault interrupt, which is a 3-prong plug. So that's how I run the computer in here. But all the other plugs are 2-prong and they're not polarized. You can flip any kind of plug in there, but a polarized plug may not fit in some of them. Okay, so we've got several things going on here. This house was built in 1930. No wonder it doesn't have a 3-prong plug. So let's talk about a 3-prong plug. That provides another grounding wire. This is just a neutral wire that goes back to ground to complete the circuit. This is an additional grounding wire so that if you did have a sudden surge, it would ground that real quickly and you may not get shocked. Okay? Say that again? Oh, okay, you're not talking to me, are you? Is that you, Valerie? Okay. Now, as I said, we're running something off the GFI in the bathroom. That's yet another safety feature. And I don't know, y'all are probably too young to remember this. Okay. Valerie, your microphone's on. Okay. Okay. Valerie, your microphone's on. So, yeah. Okay. Yeah, I should have, but she went off so I didn't see her anymore. Okay. Now, um, what a ground fault interrupt does, and I was starting to say in the old early days of television, though I don't remember the early days of television, but it was still pretty early in those days when I was growing up. Um, one of the best ways that they had to, in a murder mystery, to kill someone and get away with it is if they happen to be in the tub, drop the radio in the tub with them. Well, then they would electrocute. That was pretty gross, okay? But in most bathrooms now, in most kitchens now, and in most outside receptacles, they have a ground fault interrupt, which basically, if there's a sudden surge, it kicks it all out. So supposedly, you can't knock off somebody that way now, okay? So that's what a ground fault interrupt is. I thought they were going to show a picture on the slide. They don't, okay? So that finishes the chapter. And as I say at the end of every chapter, nothing replaces reading the chapter. So if you haven't read it already, preferably you have, but if you haven't, read it now. And then hopefully the things we've talked about will make more sense. Also at the end of every chapter, there's a summary. Now I can't see what I'm showing there because I've only got Angelita's name showing. For some reason, sometimes Zoom only shows one, sometimes it shows about 5, including myself. So I can't see myself, so I can't see what it's showing. The summary is a pretty long summary, longer than most, but this has been a pretty big chapter. Then there's a summary of equations, and this is more than most. This has 11 equations, lots of equations here, and some of these equations can be written in 2 or 3 different ways. So there's even more. The key terms, though, seems to be a fairly short list. They're listed alphabetically, but then they follow that with the page number on which that key term is first identified or defined, so you can find where those are. Then we have applying the concepts, and I say this, oh, I forgot, there's a few more key terms at the top of the next page, so it is about average, I guess. Applying the concepts, we have 50 questions, which is probably 1 or 2 more than most of them do. So they're all multiple choice. I think it's the best thing to study for the chapter test. While I'm talking about the chapter test, I will try to post it sometime this evening if I can. Now, I've got a lot of things I need to do this evening, but I'll try to remember to post that. If I don't get it posted today, hopefully I will post it tomorrow when I get back from my transfusion. And if I don't get it done, then I'll get it done as soon as I can. Okay, so watch out for that. I'll try to put it under week 6, but if they don't allow me to put something there, I'll put it under Blackboard messages. So it'll be always under Blackboard messages, possibly under week 6 as well. I'll probably have a place there for the test anyway, so you can send it back that way or send it back through message or email. Okay, those 50 questions, those will not be the same ones on the test, but they'll be covering some of the same material. Your test won't be any more than 20 questions, maybe fewer. So you see you have a lot to choose from there. These 50 questions have answers provided. So there's that. Questions for thought, surprisingly, is only 12. Usually it's around 18 or so. But for further analysis, they have 7, and usually that's around 4 to 6. So it's one more than, two few more than normal. And then they have Earth Power, invitation to inquiry. If you see something there that could give you an idea on a paper topic, fantastic. Now, if you have the big book, the parallel exercises, basically parallel with the examples they gave in the book, especially Group A. If you have the big book, those answers are in the back somewhere. If you have the smaller book, I asked them to put the answers there, but the last time I looked, I could not find the answers in the small book. So if you enjoy doing now, will your test be all multiple choice? No. There's usually 1 or 2 fill in the blanks, and maybe 2 or 3, or no more than that, actual calculations. But they're going to be pretty simple calculations. Basic things that we deal with, either Ohm's law or power formula or something like that, transformer, something like that. So be ready for a few calculations, but they're going to be pretty simple things we did in the text, okay, as we came along. Any questions? All right. Now, since there are no questions, let's see. I had meant to get the lab out here. It's not. So hold on just a minute. Do y'all need a break? I know we've been going pretty hot and heavy, and we're 5 minutes over. Do you need a break, or are you okay to keep going?
We can take a break.
Okay, let's do a real quick break. Try to keep it 5 minutes or less. I'm going to pause the recording here. All right, most of you back now. Anybody hear me?
Yes, sir.
Okay. All right. Just happens to be, can you see the lab here? I thought I was going to have to pull it up. Can you see it? Physical Science 112 Circuit Construction Kit, VC Virtual Lab, Lab11. Can you see that?
No, I see a black.
Oh, okay. My thing says I'm screen
Yes, sir.
sharing.
Sorry.
Say again?
I'm sorry. I sneezed. I'm sorry.
Oh, sneeze. Okay. I thought you said you see it. I thought, okay. Right after you saw it, sneezed. Okay, okay. Here is the lab. Can you see it now?
Yes.
Okay, good. All right. Now, let me take you to where you can get to it. And that's here under, I can't see which class I've got open. I hope it's this one. Yeah, that's the right one. Okay, so go down to weekly activities. Oh, you can't see this. Let me get this activated now. That's it. Content, Google Chrome. Okay, you can see my Blackboard now, right? Yeah, okay, good. All right, so open weekly activities. Scroll down to week 6. That's where we are right now. Okay, scroll down so you can see this. And here, oh, I don't have Lab 10 in. Oh, that's right. I don't have Lab 10. Okay. But where you can put it is under instructional materials. Okay. Not put it where I can get it. So here it is here. The one I have open is this one right here. Physical Science 111, Physical Science 112, Lab 11 new. That's what the N stands for because I did some changes to it. Here's where we open our link to good old PHET, whatever that stands for, physics, something another, whatever that stands for. Okay, so I'm going to open that. Okay, once you get that open, go to simulations. Y'all can see this, right? Right?
Yes.
Physics. Okay. Now, remember what the title was? Let's go back to that. Just to remind you, it says go to Blackboard week 6 page for this course. Go to course materials. That's where I went. Find the laboratory simulations link. We found that. Click on it. We clicked on it. Click on simulations. We did. Then on physics. We did. Scroll down to circuit construction kit DC virtual lab and click on that. So that's where we're heading. Okay. So let's go back to, there it is. Okay. Back to here and scroll down to circuit. I can't remember what it was now. Okay, we're getting close. Circuit construction kit DC. I think that's the one right there. Wait a minute. Was it that one or was it virtual lab? Can anyone read it? Because there's two of them with almost the same names. Let me go and see which one it is. Sorry about this. I have a good memory. It's just short. That is DC Virtual Lab. That's what I thought it was. Okay. So let's go back here. And it's DC Virtual Lab. That one. All right. And then we get to click on the triangle inside the circle. And it may take a little while for it to load. Okay. Things are coming up here. Now I'm going to have to move Angelita. She's sort of blocking things here, so I'm going to move her up here. Okay. Let's see what it says to do. All right. When it comes up, click on the values square at the top in the top rectangle on the right. Okay, remember that, the value square. Then click on the battery circuit symbol just to the right of the battery. Okay, and above the orange circle with a curved arrow on it in the lower right corner. That's basically going to be your reset. Okay, then build a circuit with one battery and 3 resistors in series like the figure 636 on page 1. Okay, before I do anything here, let me go on and mark. By the way, we're not doing chapter 7. If you have a big book, chapter 7 is on light. I wish we had time for it. It's great stuff, but we don't have time for it. we need to get at least one chemistry chapter in, so that's what we're doing. The first chapter under chemistry. Now, if you thumb through that, if you have the book, you can thumb through it, and anything you see there is open game for research papers or anything else. Okay, but let's go back to page 167 in the book, and this was that lab that had the figure 6-36 right above example 611, right hand column, underneath the blackout reveals pollution blurb, the green blurb that says Science and Society. That little figure right there, we're going to build something like that. Okay, it says record the voltage and each resistance value. So that's what you're going to put here. So let me go back and read and make sure. Okay, we click on the value square in the top rectangle, the battery circuit symbol, and on the right of the battery and above the orange circle, then build the circuit. So let's see if I can remember all that. Okay, y'all can remind me. Does someone have it printed off? What I was just reading? Let's see if we could. Okay, all right. And what's the first thing it says? I thought it said values. It's the upper right. Oh, here it is. That one right there. That, you see where my cursor is? It's a block that says values. I'm going to click on that so it shows the values. Okay. Now it says over here the battery symbol. Okay. So we're going to use that symbol there. Okay. So that's going to be the battery symbol. So we're going to build our circuit like the one that you see in the book. I don't know if you can have your book open at the same time. Let's do that. Okay, and it's showing a 9-volt battery there. Okay, plus side here, minus side there. Okay, now we want some resistors. So we'll take one resistor and put it here. We'll do another resistor and put it here. Another resistor and put it here. Okay, wire, we'll take a wire and go here. We're going to build us a circuit. Okay, I need to turn this. I wonder if I can remember how to turn it. Okay, I think I'll do, yeah, that works. Okay, and then one more wire here. I probably should have done this. Okay, and then we'll do another wire over here and turn it down. Oh, look at that. I didn't know I could stretch it out like that. Okay, I could have made that a lot prettier picture. Okay, all right, so let's record what we've got. We've got now they're showing electrons moving. That's why they're minus signs here. In reality, we usually talk about the conventional current, which would have plus signs moving in the opposite direction. It doesn't matter, okay? But we'll go with what they've got here, okay? So on your piece of paper, what was your voltage? 9.0. What was your R1? Anybody? And that was 9.0 volts. R1 was 10, maybe 0.0 ohms. R2 was 10.0 ohms, and R3 was 10.0 ohms. Okay, first thing it asks, calculate the total resistance of the circuit Okay, so do that first. What's the total resistance of that circuit? Pretty easy, I think. It's a 30, absolutely. You add your resistance because it's a series circuit. So your effective resistance was 30 ohms. Okay? Now it's time to calculate the resistance. Okay? I mean the current. Okay? How do you get current if you know voltage and total resistance? Divide what? Yeah, V, which is 9, divided by I. You're looking for I. So divided by your total resistance, which is 30, right? And that gives you how much current? Anybody? 0.3 what? Current. No, ohms is resistance. Current is, no, voltage is volts. No, 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 no. Amps, amps. Okay. Named after Louis Ampere. Current is measured in amps. Okay. Now, it says the voltage drop across each resistor. Okay. Now, let's go and look at that again. Okay. You have, you know your total current here, you just calculate it, is 0.3 amps. Okay, it's all going through every one of those resistors. So the voltage drop across here, voltage is current times amp, times resistance, IR, that's Ohm's law. That would be 0.3 times 10. I can do that one in my head. What is it? 3. 0.3 times 10. 3. And 0.3 times 10 again? Okay, so those three are 3. And guess what? They add to be 9. Sure enough, there, the total voltage drop has to be the voltage supplied by the battery. Okay, so that was our next 3 blanks. Okay, voltage drop across one was 3 volts, 3 volts, 3 volts. They add to be 9 volts here. Oh, leaving the other values as they are, increase the voltage. Okay, yeah, I was just telling you, add those 3 together, you should get the same voltage you had there. We did. Okay, now leaving the other values as they are, increase the voltage and record the new value. So let's go back to the simulator, the whatever you call it. Okay, we need to increase the voltage. I'm trying to see how I can do that. Oh, do y'all rather see the electron current or you rather see conventional current? It really doesn't matter. I'll just show you how conventional current looks. This is pretending they're positive charges and then they go through this way. It doesn't matter at all. Okay. Now, I need to increase, let's see, I'm trying to remember how to increase this. Oh, tap the circuit element to increase. Ah, there we go. What you want to increase it to? You choose.
27.
27. Okay. Let's see if I can get to 27. There we go. Hit it. Okay. 27 volts. Okay. So let's go back to our page. And that now voltage is 27 volt. Right? Now, calculate the total resistance of the circuit. You left all those the same, right? So the total effective resistance is still
9.
no resistance. Add the
30
three.
ohms.
30 ohms. 30 ohms. Okay, this was 27 volts now. This is 30 ohms. Now we have to calculate the new current. And you remember what current was?
3
Ohm.
amps.
No. Okay, no. Not what it was. What the formula for current is.
Oh, okay, I'm sorry.
Yeah.
Yeah, we divide. I don't know. I forgot.
Oh, you just did it. Ohm's law. V divided by R. So our new V is 27. 27 divided by our 30, right? Whoops. My calculator is messing up. I'm messing up. 27 divided by 30, still 30 ohms. What do you have now?
0.9 amps.
Yes, 0.9 amps. Okay. Now we need to calculate the voltage drop across each of our resistors. Okay. So let's go back and see what those are. Okay. Your current was 0.9 amps, right? That's what's moving here across each resistor. Okay. And voltage is current times resistor, so that is 0.9 times 10. And what does that give you?
9.
9 watts.
9 volts.
Eh? Oh yeah, 9 volts. Yeah, voltage drop. Yeah, 9 volts. This one would be
9 volts.
9 volts. This would be,
9 volts.
and those add to be.
27.
Hey, that works out, doesn't it? Okay.
Yes, perfect.
All right. Let's go back and see what's the next thing being asked. That's just a check. You don't have to do that, but it's a good check to do. Okay. So we did this one. This was 27. No. This was still 30 ohms. That was our 0.9 amps, 9 volts, 9 volts, 9 volts, and that added to 27. All right. Now I'm going to screw this up a little bit. Now, this time it says, leaving the other values as they are, increase the value of R1 and record the new value. Okay? I was starting to go to my calculator and do it. That doesn't make any sense. Okay? So let's go back here, and y'all can play with this to your heart's content too. Which one of these you want to call R1? This one here or that one there? It doesn't matter to me. This one?
Yes.
Okay. Let's click on that. It was at 10 ohms. We want to increase it. What you want to increase it to?
17.
17. Nice round number. There, I hit it on the nose. Okay. We'll leave everything else the same. Now, what does it ask for us to do? It says that's your new R1, 17 watts? Ohms. Calculate the total resistance in the circuit. What would that be? This is series. Or no, you didn't change them all. You only changed that one.
Oh, we didn't change them all. Okay.
No.
20. No,
37 ohms is the new resistance. Very good. Okay, so that's what you put here. The new resistance RE, when this changed to 17, this changed to 37 ohms. Okay, now since you know your voltage was 27, right? Your effective resistance is 37. How do you get your new current?
Divide the ohms against the voltage.
Okay, what do you mean against?
I mean, divide the ohms by the voltage.
No, not by, into. Excuse me, I'm so sorry. That must have been loud. Okay, it's V over R. So voltage 27 divided by effective resistance 37, didn't you say? Hit equal, and what do you get now? Ooh, weird looking number.
0.72?
I would round that up to 0.73. I get 0.7297, blah, 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 blah. So let's make it 0.73. It's 0.73 what? Amps. Excellent. Okay. Now we need to do the voltage drop across each resistor. So this V1 is going to be the voltage drop across that resistor. So how do we get voltage drop? Or voltage? Ohm's law. Anybody?
Multiply the amp
By the volts, exactly. And I think you got 0.73 was our current, right? And multiply that by, wait. Voltage drop would be amps times resistance, because you're looking for voltage. Amps times resistance. So 0.73 times 17, right? V is equal to I.
right?
No. Across resistance 1. R1. Okay. 12.4. I would just leave it 12.4. Okay. It'll be close enough. Okay, we do that for the second resistor. That was 0.72 was your current times that resistor. That's 10. Are you still there? Okay, good. Okay. So what's your voltage drop across the second resistor?
12.4.
Okay, wait.
Oh no, because they didn't change.
Wait. Okay, wait. Okay. To get that first one, you do your current. See, the current goes through all of them. The current times the resistor. So that was 0.72 or 73, wasn't it? Did we round this? 0.73 times 17, and we got 12.41, you said, right? Okay. We can write that down if you want to. But across this one, it's not 17 anymore. This one's only 10. So 10 times 0.73 would be 7.3. This one would be
7.3.
okay, so you got 12.41 plus 7.3 plus 7.3. We should come up close to 27. Oh, did we ever come up close to 27? 27.01. That's just round off error. Okay?
Right.
Okay?
Okay.
So you got that? So here we have, and all I'm saying are numbers. I really should be saying units as well. Let's see, this was 17 ohms. Effective resistance was 37 ohms. Current was 0.73 amps. V1 was 12.41 volts. 7.3 volts. 7.3 volts, right? Is that okay? All right. Everybody got it? Are there any questions? Please ask questions as we're going so we can get it straight as we're going and not get very confused, if possible. Is this making sense?
Yes,
All
it
right.
is. You're
Okay.
getting it.
All right. Ohm's law all over the place here. Okay, let's now, leaving other values as they are, increase the value of R2. So let's go find our thing again and go to R2, click on it, and I have to click on it again, I think, or maybe click on this. Here we go. What you want to change it to?
20.
20. Okay, let's see if we can get up to 20. Oh, look at that. Hit it right on the nose. Okay. Now, you still got 17, you still got 20, still got 10, still got 27 down here. Okay. Just trying to remind myself, because let's go back and see what it's asking for. Okay. Now, if y'all want to use different numbers, you're certainly welcome to do so. It's your lab. You can do it however you want to. So the one you chose was R2 was equal to 20. 20 what? Anybody?
Volts.
Nah, R is not in volts. V, volt.
Constant.
Say again?
Let me see what you said. Okay.
20 ohms. Okay. R2 was 20 ohms. Okay. Now we have to calculate our effective resistance. So let's go back and look at our picture and see what we get. Effective resistance for a series circuit, you do what? Oh, here comes Dre. Good deal, Dre. Glad you're here. Okay. All right. Well, now finally Valerie has a little help there at the bottom of the alphabet, but okay. But she and Dre are having to hold it up all by themselves there. That's too bad. Okay. Now, what was our effective resistance here? Dre, we're doing the lab. If you go to Blackboard, this course, Physical Science 112, go to week 6, go to instructional materials, and look for Lab 11. It says PHS112 little l 11N, I think it is. That's the lab we're working now. And right above that, under you'll see the link to the FET, and you can click on that and follow the directions on your lab sheet, and you'll see how to get to here. We've already started on the lab. I'll show you where we are as soon as we get off this. Well, let me show you now. Have you got the sheet either in front of you or on your screen or something like that? This is what the lab sheet looks like. We did the beginning of it, and I didn't number them. I probably should have. We've just changed R2 to be 20, and I was waiting for, oh, and someone did answer, ohms. R2 is 20 ohms. So this is where we are right now. So if you found that on the lab sheet, this is where we are. Now, you can get with somebody. This is a lab. You can work together on labs, of course. Work together, find out what you missed. Or, as soon as, well, I don't say as soon as, sometime this evening, Before I go to bed, I'll check and see if this is loaded on Blackboard yet. And if it has, then you can go to the uh, Blackboard, I'm sorry, load it onto YouTube. Go to the YouTube link for this course. You can find that under week 1. It says recorded lectures or whatever it calls it. There's a YouTube link there. Um, Click on that and then go to the lab that I'll load. It's going to take it. See, this class has already gone almost 3 hours, and so it's going to take it probably at least 3 hours to load, and then sometimes after it loads, then I'll move it to the playlist. So it'll be late this evening or sometime tomorrow. Okay, and you can pick up the ones you missed, or you can get with someone in the classroom in the class now and pick up the values that you've missed so far. But here's where we are, where it says leaving other values as they are, increase the value of R2 and record the new value, and that's 20 ohms. Okay, now we were looking for effective resistance, so I'm going to go back to the FET. Okay, and I don't think y'all answered that yet, did you? What's the effective resistance? Okay, I got your concept, but you said the words wrong. You add the resistors together to get the effective resistance. I think that's what you meant. Okay. Okay. So when you add these together, what you get is effective resistance. Anybody? You add these together because they're in series with each other. It's sort of like you have one big resistor that's the total of these three. What does that add to? 47. Say again. And what is that called? Georg. Whose law is it? Ohm. Georg Ohm. Ohm's law. So these are ohms. That's what that omega stands for, is ohms. That would be, like you said, 47 ohm is your effective resistance. So that's what we put here. Okay, well, I'm not quite there yet, right there. Effective resistance here, 47 ohms. Okay, what should be your current then? How do you get current?
By dividing the resistance by the voltage.
Okay, not quite. Into the voltage. R over, yeah, E over R. So that would be your voltage was 27, wasn't it? Volts.
Yes.
Divided by, what was that total resistance?
47.
47, what units?
Ohms.
Ohms, excellent. Divide that, and how much current do you get?
I got 0.57 amps.
That's exactly right, or it's rounded off to 0.57 amps. So that's what we put here. The current here is 0.57 amps. Okay, now we're going to take that and go back and calculate the voltages across each resistor. The voltage drop across each resistor. So remember, it's 0.57 amps. So, I mean, 0.57 amps. And we're going to do the voltage drop across this one. So 0.57 times 17 ohms. This is how you get voltage is equal current times resistance, Ohm's law. And that gives us
9.69.
Yeah, okay, something like that. You could round that to 9.7 probably. Okay. And then the next one would be I don't remember my current now. I didn't write it down. 0.57 or something like that. What was the current?
0.57 amps.
Okay, times 20. And that would be something on the order of 11.4. No, yeah, I think so.
Yeah, 11.4.
Okay, that would be the drop across R2. Okay, plus, or the next thing we'll do is 0.57, was that right? That was your current, times 10 would be 5.7, right?
Right.
Okay, and what does that get us? Okay, so those are your three um, voltage drops. Now, with those three voltage drops, let's add
26.8.
26.8. That's pretty close to 27. You're absolutely right. That's just a check. You don't have to write that down, but it's a really good thing to do because these three had better add to be wherever we wrote it down, right up here. That one. Goodness, my wife brought some good smelling food home. I don't know what it is, but it's smelling awfully good. I may have to close the door. Okay, so let's move on down. Okay, and leaving the other values as they are, increase the value of R3. So let's go back to our circuit construction kit, and we're going to increase the value of this one. What do you want to increase that to?
15.
15? Is that what you said?
Yes, sir.
Okay. Oh, whoa, look at that. I hit it on the nose. Okay. 15 ohm resistor there. Okay. And what's the next thing it asks for? What's the total resistance or effective resistance of that series of resistors? Isn't that what it asks for next?
Yes.
And what does that give you? Anybody? 52 ohms. Excellent. 52 ohms. Okay. Next question, I think, says what's the current through that? And what would that be? I'll go have to drink me something. It's smelling so good downstairs. And I was out of water. It's too bad. What you get? 0.52 amps. Excellent. 0.52 amps. Okay. Now, what's the next question? What's the voltage drop across resistor 1? How do you get that?
Volts.
8.84 volts. Perfect. Okay. And then the next one would be, I can't remember what was my voltage. I don't have it written down. I mean, I got the voltage. What's the resistance? Oh, no, I've got it all, don't I? No. The current. Yeah, what was the current? That was what? 0.52, was it?
Yeah, 0.52 amps. Yeah.
Okay.
It's gonna be 10.4 volts.
Exactly, plus 10.4. Okay. All right, and then the next one,
We 7.8 volts.
7.8. Now I'm not checking those. I'm trusting your word on it. Okay. 7.8. Let's see how it comes out. Oh, that came out pretty close to 27, so I'd say your calculations look pretty good to me. Okay, did everyone get those? I didn't get back to my screen here. Okay, there it is. So we had, here's where we were. We changed that to 15 ohms. Our factory resistance was 52 ohms, wasn't it? The current was 0.53 amps. And then the voltage across one, I can't remember what they were now, but y'all got them, right?
It was 8.8, 10.4, and 7.8.
All right, excellent. Okay. Now, what we're going to do, go back to the FET and click on the orange circle, which is with the curved arrow. That's going to change everything. Okay? In the lower right corner of the screen. Okay, again, click on the value square, so we're going to have to do that in the top rectangle on the right. We'll click on the battery symbol, just as we did before, and then above the orange circle with the curve, oh yeah, that's where the battery thing is, okay? Then we're going to build a circuit with one battery and 3 resistors, this time in parallel, like 6.37 on page 169, okay, in the text, okay? And if you don't have this text, 6-30 would work, okay? We'll record the voltage at each resistor value, okay? So I hope I can remember all that. Y'all guide me through it if I forget, okay? So first thing we're going to do is go over here to the bottom right and hit the circle, okay? Now we need to put the values in, so go up to the top right and click on values. You see that? Okay. Now what we're going to do is build the circuit like it is in the book, okay? Rather than hold my calculator here and risk dropping it, which is my phone, I'm going to plug it back in and set it down somewhere safely. Okay. All right. So let's start with the battery right here on the right. And that just gives you the battery symbol. So we're going to get the battery here and bring it down here. That's starting off as a 9-volt battery. Okay. Now I'm going to start with conventional current. I didn't say do that, but I just like it a little bit better. Okay. Now we'll start with a resistor and place it here. We'll go a second resistor and place it here. And we'll go with a third resistor and place it here. That's pretty close to what they have in the book. And then we'll have some wires connecting them. Okay, and I'll connect it here and bend it up here. I wonder if I can carry it to all 3. It looks like I can. Look at that. And let's do another wire and do the same thing on the other side. I hope this is working. Okay. All right. I think if that doesn't work, I'll come back and do individual wires. We're going to try it. Okay. Now, let's go to our back to our page. All right, where were we? Here. Okay. Record the voltage. What was the voltage?
9.0.
9.0 volts. What was your first resistor?
10 ohms, 10.0 ohms.
And second resistor?
10.0 ohms.
And then the third resistor. Okay. Now it says to calculate the total resistance of the circuit, which I called effective resistance. I don't know why it said total here. I think because the book used it. And then we'll do the current, and then we'll do the current through each resistor. Okay. Now I'm going to have to get my calculator back. Okay. Now, this is a parallel circuit. Okay. And with parallel circuits, this is a little stranger. Okay. The effective resistance, I wish I could write on the slide. Maybe I can. Maybe I can on this slide. Let me see if I can. Maybe I can't here. Let me try it. Okay. No, I can't. Okay, I was afraid of that. Okay. So sorry about that. I knew I couldn't on the FET. I couldn't remember if I could here. Oh man. Okay. Okay. Hopefully I've gotten rid of all that mess. Okay. So let me put this aside then. All right. Remember how we do this? 1 over R1 plus 1 over R2 plus 1 over R3 is equal to 1 over RE. Okay, so here's how we do it. I don't know if you can see my calculator. You have to turn it sideways if you got a phone. Okay, if you got a scientific calculator, you're in good shape. So you do the 10, that was your first resistor, and then find your 1 over X key or your X to the minus 1 key. Okay, and press it. That should give you 0.1. Has everybody done that? Let me know. Plus, say that again.
Say it one more time.
Okay, let me start over. All right. Your first resistor was 10, so enter 10. Oh, now some of you may have different syntax on your things, but I think it'll work that same way. Enter the 10, then you look for the key that's your 1 over X key. I don't know if I've got it so you can see it or not, or it's X to the minus 1. One of those two keys, 1 over X or X to the minus 1. Do you find that on your calculator or on your phone? Anybody? I just can't see where my camera's shooting, so I don't know if I'm on it or not. Okay, if you can't do that, you can do it the brute force way. 1 over 10 plus 1 over 10 plus 1, and when I say over, divided by 10, equal, and then do 1 over that. That will work too. The easier way is do 10, then the 1 over X key, that gives you 0.1, plus 10, press the 1 over X key, that gives you another 0.1, plus 10, 1 over X key, and that gives you another 0.1, equal, and then that one you do another 1 over X key here, and that gives you what resistance. Now if you don't have the 1 over X key or you can't find it, it's 1 divided by 10 plus 1 divided by 10 plus 1 divided by 10, and then do 1 over your answer, however you do that on your calculator. Does anyone get an answer yet? Help me somebody. Okay. I'm going to go back and do it the second way. I don't know if you can see me working, but I'll do it. Okay, 1 divided by 10 plus 1 divided by 10 plus 1 divided by 10 equal, and you should come up with a 0.3 then, okay? And then divide that answer, let's see if that's right. I would say write that answer down, 0.3, and say 1 divided by 0.3. And when you do that, what do you get? Anybody? Was anyone following me?
Yes.
Okay, what do you get as an answer?
I'm pretty sure it's not right.
Okay, what is it?
I got 17.
No, you're right. 3.33, that is it. Now, were you doing the 1 over x key, or were you doing the 1 over key stuff?
1 over. I don't have that key.
Oh, you don't? Okay. How about the one who got 17?
1 over.
1 over. Okay, let's start back at the beginning then. Okay. It's 1 divided by, no, I'm sorry. Start over. 10, no, I was right the first time. 1 divided by 10, okay, plus, that should give you a 0.1. 1 divided by 10 plus, that should give you 0.2. 1 divided by 10 equal, that should give you a 0.3. Okay, that's 1 over your effective resistance. So you take that and do 1 divided by 0.3 equal, and you should get 3.333. Okay.
Yep, I got it.
Okay, good. So you stop, I'd say just 3.33 will do. Okay, so that's your effective resistance right here, isn't it? Isn't that where we are? Yeah. Okay. Now, the first one says, what's your total current? Okay. The current through the circuit. Okay. Let's go back and look at it. Okay. Because it's been a while, we may have forgotten what it looks like. Your voltage in this circuit is 9 volts. Your effective resistance is 3.33 ohms. I hope you put ohms down there for that one. So, what is your current? V divided by R. Okay, so that would be 9 divided by 3.33333. Okay, so what did you get? Any? 2.7 amps is right on the money. Very good. Okay. Now, the next question said, okay, anyone have any questions on that? I'll be glad to answer if you have questions. Okay, that's your I. Now, what we have to do is figure out what's the current through the first resistor, the second resistor, and the third resistor. We know the voltage is the same, 9 volts, and we know what the resistors are, so we have to calculate the currents now. So let's go back and do that. So what is current? Voltage divided by resistance. So that's 9 divided by 10 equal what you get. Pretty easy, you could do it in your head. 0.9. And then 9 divided by that 10 is also 0.9. And 9 divided by this 10 would be 0.9. You add those 3 0.9s together, and what do you get? 2.7, right? Okay. And that would be amps. Every one of those was an amp because those are currents, right? So, see if I can remember them. This was 3.33 ohms. This was 2.7 amps. This was 0.9 amps, 0.9 amps, 0.9 amps. Your check is add those three together and you get 2.7 amps. Okay? Now, leaving the other values as they are, let's increase the voltage and record the new voltage. Okay? So let's go down here to our circuit kit and let's do a new voltage. What you want to go to? Anybody? 12 volts. Okay, let's see if we can go to 12 volts. He's got a car battery. Okay, there we go. I hit it. 12 volts. Okay. Now I think the next question is going to be, let's go, I think it's calculate the effective resistance, isn't it? Yeah, we get to 12 volts. Okay. Guess what? We didn't change anything in the resistors, so your total effective resistance is the same as it was before. We didn't change the resistance, we only changed the voltage. So effective resistance is still 3.33 ohms. Okay, now with that in mind, let's calculate the new current. Okay, so go back here to the circuit thing, and we know the new voltage is 12, and the new effective resistance is, that's all three of these together, 3.33. So the new current will be Ohm's law, voltage divided by effective resistance. So that would be 12 volts divided by 3.33333, right? Well, you can stop wherever you want to. Okay, and hit equal, and what you get approximately for your answer. Anybody? 3.6 amps. Very good. So that's what we put here. Your total current is 3.6 amps. Right there. Okay? Now we're going to calculate the current through each of your resistors. Okay? So let's go back up. Remember, 3.6 amps was your total current. Your voltage is, well, we'll see what the voltage is. 12 volts, and that should, so that's going to be pretty easy to do. What is your current through this one? Current is voltage divided by resistance. So that's 12 divided by 10. What's that? Anybody? It's real easy. 12 divided by 10. 1.2 watts. Amps, absolutely. And this one, the next one would be 12 divided by 10, which is? And the next one would be 12 divided by 10, which will be? Okay, and just as a check here, what happens if you add those three together? So that would be a 1.2 amps, that would be a 1.2 amps, that would be a 1.2 amps. Add them together and you get? 3.6 amps. And isn't that what we had right here? Yes, yes, yes. Okay. Wait, I was down here. Sorry about that. I was on the wrong line. But you did get 3.6 here. Okay. Now, scroll down a little further so I can get on the right place. This turned out to be a long layout, didn't it? Okay. Leaving the other values as they are, let's increase the value of R1 and record the new value of that R1. So let's go to our kit and we're going to change R1. You want this one to be R1? You okay with that? Why? There we go. What you want that resistance to be? Anybody? Anyone? Let me know something, somebody.
Hey, sorry, what was the question? I had to use the bathroom.
Oh, okay. We're back on our circuit here. We're going to leave our 12 volts like it is, and the two 10s like they are. We're just going to change the value for R1.
How about 25?
25. Okay, we got a 25 coming up. Let's see if I can hit it. There we go. There's a 25. Okay, I'm pretty sure the next question is going to be calculate the effective resistance of these now. Okay, remember how we did that? 1 over this plus 1 over that plus 1 over that, and whatever answer you get, 1 over that is your effective resistance. Now if you have that reciprocal key, use it. It makes it so much easier. But I'll do it the long way here. So it'll be 1 divided by 25. That should give you 0.04. Okay. And I'm going to add as I go, plus 1 divided by 10. That's going to give you 0.1, right? We did those before. Right?
Mm-hmm.
Plus another 1 divided by 10. That should give you another 0.1 equal, and what do you get? 0.24. Okay, but you don't have to write an answer for that one. Okay, now you take that and do 1 over that. Okay, so that's going to be 1 divided by 0.24. And what do you get?
4.16.
Yeah, let's round it to 4.17. Okay, so that's what we put right. I hope I was doing the right one. Okay, we increased that to 25 ohms, wasn't it?
Yes.
And then our effective resistance was amazingly 4.17 ohms. Okay, And with that as our effective resistance, what is our current? I. Well, what was our voltage? What did we increase that to? 12 volts. So to get I here, we do 12 divided by this 4.17 or whatever. Okay, so you get something like,
2.87.
okay, yeah, I got 2.88, but 2.87 will do. That is your total current. So what units would that be?
Amps.
Amps. Excellent. Okay. Now, let's go back to our kit, and we're going to calculate each of the individual amps. And remember how we did that? It was voltage divided by resistance. So the first one's going to be 12 divided by 25, 0.48. 12 divided by 10, that's pretty easy. That would be 1.2. And the other 12 divided by 10 is?
Also 1.2.
Okay. So let's just add those together and see what we get. Pretty close to 2.88 or 2.87, isn't it?
Yep.
Yeah, so good news. That sounds like we did it right. So here, let's go fill them in. Y'all have to remind me what the numbers are because I have a good memory. It's just short. Okay. Where are we now? We changed R1. RE was 2.88. Was that right? I was, oh, what was, no, I was 2.88, wasn't it? Yeah. And I1 was 0.48 maybe? Was that right?
Yes.
Yes. And I2 was 1.2 and I3 was 1.2. Got it?
Yes, sir.
All right. So let's leave all the others the same and increase R2. So let's go back to our, let me see, how long is this? I don't think it's that much longer. Okay. Let's go back to our kit and we're going to increase R2. Okay, what you want to increase it to? Wait.
13.5.
Okay, nice round number there. Let me plug in my phone just to keep from running it down any further than I have to. Okay, we're going to increase that to 13.5. Is that what you said?
Yes, sir.
Okay, let's see if I can get it. 13.5, there it is. Okay, I didn't know I would be able to get it that well. Okay, now that didn't take me as long as I thought it would. So what do we have here now? I think the next question is what's the effective resistance? Is that it?
Yes.
Okay. Effective is, remember it's like before. It's 1 divided by 25, which is 0.04. Okay. And then I'm going to add, well, yeah, add to that 1 divided by 13.5, and I'm going to add to that 1 divided by 10, which is 0.1, and hit an equal sign. Now that gives me something like a 0.21407, something like that. Okay. I'm going to turn mine sideways and use my 1 over x key because otherwise I'll mess something up. Okay, and that gives me an effective resistance of about 4.67 maybe.
Yep.
Okay, so that's our effective resistance here. Let's go back and plug it in. Where are we? We just changed R2, so our effective resistance, RE, was about 4.67. Got it? Okay. With that in mind, let's calculate our I. Does anyone remember what the voltage is? 12. Okay. So I'm going to do divide 12 by that effective resistance, and what do you get? Okay, yeah, pretty close to that. I would have rounded 2.57, but that's okay. Whatever you want to do, that's going to be fine. So that's your that's your current, the total current in the system. That's what you put on this line here. Now for the next three, I'm going back here because it's much easier to do it looking at this, because I can't remember. The current through each of these resistors is the voltage divided by each of those resistors. So the first one is 12. Let's see. Hold on just a minute. Our effective resistance was this. No. I've confused with what. Yeah, no, that's the current. That's the current. Okay. I believe someone's got it. Yeah. Never mind. Okay. Resistance of each of these, the first one would be 12 divided by 25. Whoa! I left something on. Okay. 12 divided by 25, which I got to be something like 0.48. Is that what you got?
Yep.
Okay. Now I'm adding as we go. Plus 12 divided by 13.5. Whoops. Left off my decimal place. That would really throw it off. Okay. Does anyone have that?
1.37.
Okay, you're adding as you go too, aren't you?
Yes.
Okay. And then you add 12 divided by 10 would be 1.2. And that gives us 2.57. Isn't that what we had before? Now, I didn't calculate the individual ones. I did two of them. I did the first one, I did the last one. I didn't do the 13.5. You need to do that. 12 divided by 13.5. Oh, I didn't hit my keys right. My fat fingers don't work well. 12 divided by 13.5. That one was 0.88 or 0.89. Okay? So, does everybody have those numbers? I know I'm going maybe a bit too fast here.
I didn't get those numbers. I'm sorry.
Okay. All right. Let me see if I can remember. It's going back. Okay. Did anyone have them?
I do.
Okay. Call them out.
First one's 4.67.
Okay.
Is 2.57.
Okay. Tell me which blank are you giving first?
The RE.
RE. Okay. RE was 4.67. Is that right? Okay. Next.
I is 2.57.
2.57. I1.
0.48.
Perfect. And those are amps, by the way. The first one was ohms. This one's amps. This one's amps. Next one.
I2 is 0.89.
Okay. 0.89 amps. And I3 was
1.2 amps.
1.2 amps. Okay, exactly. And then you add these three together to check and see if you get I. Did you?
Yes.
Yes, very good. All right. Now, leaving the other values as they are. Oh, no, don't tell me we're almost at the end. We're having so much fun. Okay, let's go back to our board here and construction kit, and let's change this last resistor. What you want to change it to?
18.
18. All right, right on the, there we go. Hit 18 on the nose. Okay. And I'm pretty sure the first question is going to be, what's your effective resistance of that circuit? Okay. Wait, I just was turning off my thing. Okay. Now, effective resistance would be 1, wait, yeah, okay, divided by 25. We already had that before. 0.08, right?
Let's see. I got 0.04.
Okay, I thought that was wrong. My calculator phone doesn't do a really good job. Okay, 1 divided by 25 is 0.04. You're right. Okay, now let's add as we go. Plus 1 divided by 13.5 plus, wait, mine screwed up again, sorry. I have to go back to the beginning. My fat fingers don't work well on this. 1 divided by 25, that's 0.04, plus 1 divided by 13.5, plus, and that gets me up to 0.114 or so, 1 divided by 18 equal. What you get?
0.17.
Yeah, that's about what I got too. And then I'm going to 1 divided by that gives me,
Messed up. 5.88.
okay, pretty close. I got 5 point. I'm just going to round mine to 5.9 because I don't want to write down so many digits. Okay, 5.9 approximately. Okay, now is someone else coming into class? I just saw something move here.
No, I just sent out a chat to the class.
Okay, is there something that I need to hear too?
No, sir.
Okay, fine. All right, are y'all following it okay, or is this going too fast?
We're following.
Okay, good. So we got our effective resistance to be about 5.9 watts. Anybody? What units?
5.9
Ohms, excellent. Okay, so that's what we put, if I can get the thing to come up, right here. We changed this to, what was it, 18? Was that right? R3 was 18?
Yes, sir.
Okay. Now, effective resistance was about 5.9 ohms. This was ohms, that's ohms. So now we calculate the current in this. Okay? Well, we know the voltage was 12, right?
Yep.
And we multiply that by, or divide that by your 5.9 or whatever you had there. And what do you get?
2.03.
Ah, that's what I got too. I may even just call that 2. Okay, but you can do 2.03 if you want to. That's fine. Okay, so that's your total current. Just remember that. Okay, because the rest of these are going to be pretty easy to calculate. Okay, because you get your current through this one by your voltage divided by your resistance. So that would be 12 divided by 25. That gave you, same as we had before, 0.48. And then your 12 divided by 13.5, we already had that one.
0.89.
0.89. And then your next one was 12 divided by 18. That's the new one here. And what do you get?
0.7.
Yeah, it's 0.6667. Yeah, right. Okay. Add those three together, and what do you get? This is just a check. You don't have to do it, but it's a good check to do.
2.03 amps.
Ah, look at that. Exactly like we were expecting. Good deal, folks. Does that make sense?
Yes, sir.
Okay. Was this lab worth it?
Yes, sir.
Okay. This was Ohm's law, but this time you built your own circuit and you made your own variations there. The last one was sort of fixed for you. This one we played with a lot. And guess what? If you don't like the numbers other people did, you can do it yourself. Play with it yourself. See what you get. Whatever you turn in, I'll check it and make sure that's right. But we got it. Are there any questions on the lab?
No, sir.
Okay, anybody else? Did your chat come through okay? Everybody's got what you got? Okay, is it all right for me to stop sharing then? Well, we got it up. I can answer any questions. Are there? Okay, so I'm going to stop sharing. Just did. I didn't mean to that fast. Okay. Anything else before I end the meeting for us all? Now, let's go over just quickly how we're going to end the term. Okay? We've just done Lab 11. Okay? That's the last lab we'll do in Chapter 6 because we're through with Chapter 6 now. So what we'll do, I hope all of you realize this now. Okay, for those who came in late, let me say this. I will not be available first thing in the morning. Normally I have office hours 8 to 12 on Fridays. I've got to go get a blood transfusion tomorrow. Okay? The treatment that I had a month ago knocked the white cells, from 140,000 down to 1.4 thousand. Okay? It did its job. But at the same time, it wiped out a bunch of red cells. It wiped out a bunch of platelets, hematocrits, hemoglobin. I can't think of the other thing now. Neutrophils. It knocked everything. It really hit the white cells. That's what it was designed for. But it wiped out a bunch of other stuff too. So that's why I've been